We welcome our resource person, Dr. M. Arivanandan, Anna University.
Good morning, sir.
Good morning, sir.
I'm ready now. So whenever you want, we can start the program.
First session 1 will start at 9:30. A very good morning to all of you. Let us start the first session of today's program. I request Dr. A. Mohamed Salim, Associate Professor of our department, to introduce today's resource person for session 1. Good morning to all. Today we have a topic, oxide thermoelectric materials for energy harvesting. So this is a very important topic. You know that so nowadays the new materials are arrived because of we are forced to switch over to the non-conventional energy to improve the efficiency of the materials. So that is why the topic is selected the oxide thermoelectric materials for energy harvesting. So this lecture will be going to deliver by Dr. M. Arivanandan, Anna University, Chennai. Dr. M. Arivanandan is a professor at Center for Nanoscience and Technology, Anna University, Chennai. He worked as assistant professor at a Research Institute of Electronics, Suzuka University, Japan, before joining as associate professor at Anna University, Chennai. He has been a visiting associate professor at ICC IMR, Tohoku University, Sedai, Japan. He was as postdoctoral research at the Institute of Material Research, Tohoku University, Japan for 2 years. He has completed PhD in physics at Allahabad University, Karaikudi for his work on unidirectional growth of novel organic crystals. He has started his career as a teaching assistant at the Department of Physics, Allahabad University, Karaikudi in the year 2002, and he is now professor at CNST, Anna University, Chennai. He has more than 19 years of research experience in physics of crystals, photovoltaics, thermoelectrics of bulk and nanomaterial, and defect engineering in silicon and silicon germanium alloy semiconductors. He has established the Hall effect measurement and Seebeck coefficient measurement facilities at Anna University for thermoelectric research and have made available for researchers from different institutions. He has published more than 187 papers in international peer-reviewed journals, 51 papers in conference proceedings. He has presented more than 400 papers in international national conferences, seminars, and workshops. In addition, he is holding 2 Japan patents on defect engineering in photovoltaic silicon, 1 Indian patent. He has delivered more than 100 invited talks, lectures in various national, international conferences at various countries. He has guided 7 PhD scholars and 4 research scholars are working under his guidance. His group is mainly working on nanostructured alloy semiconductors and oxide semiconductors for energy conversion and energy storage applications. He has organized 7 national international conference workshops. In particular, he has organized the first international conference on applied science and technology in Tamil Anna University, Chennai during September 2017. He is a board of study members for various institutions, including Wells University and Loyola College, Chennai. He has been the principal investigator and co-investigator of several sponsored major research projects with a total grant more than 17 crore rupees funded by various organizations such as DST, SERB, STARS, MHRD, MUXT, Japan, GIMRT, Japan, JAXA, Japan. He has also undertaken various minor research projects from various organizations. Currently, he is having 2 national projects and international projects. He is a member of several academic and professional bodies in the field of material science and engineering. And he is the recipient of several awards and recognitions. Some of them are listed. It is Distinguished Research Award by Anna University in the year 2001. Then ISPA Dr. S. Gunasekaran Award by Indian Spectrophysics Association in the year 2020. Coordinator Erasmus Plus project with the University of West Africa, Greece. The Young Scientist Award in the year 2018 in Physical Science by Academy of Science, Chennai. And Young Achiever Award, Yelavenil Science Association, Chennai in the year 2018. The Grant in Aid under Early Career Research Award, SERB DST India in the year 2016. And JSPS Young Scientist during 2014 and 16. Grant in Aid from MEXT, Government of Japan. And JSPS Young Scientist B during 2010 and 2012, grant in aid from MEXT, Government of Japan. Then editorial board member of journals Crystal Structure Theory and Application from August 2012 onwards. So with this introduction, I invite Dr. M. Arivanandan to deliver the lecture in this topic, oxide thermoelectric material for energy harvesting. So welcome you, sir.
Thank you, sir. Thank you for your nice introduction, and I hope my audio is clear, right?
Yes, sir.
Okay, fine. So, first of all, I'd like to thank the organizers of this DP program, Dr. Jamal and his team, and ISPA, for inviting me to give a lecture on oxide thermoelectric in this program. So let me share my slides first. Yeah, can you see the slides now?
Yes, sir.
Hello.
Yes, sir. It is visible, sir.
Okay, okay. Okay. So today I'm going to give a lecture on this oxide thermoelectric materials for energy harvesting applications. Actually, this is the kind of collaborative work we both are doing, myself and Professor D. Anbaragan from University of Madras, Department of Nuclear Physics. And to start with the background of this thermoelectric research, as your professor during the introductory address, he said that the importance of this thermoelectric. So thermoelectric is quite important, and people are working on this field on various kind of materials, mainly because of the energy and the environmental issues. So the first environmental issues is, as we all are aware of that, the global warming, right? So we are facing this kind of global warming issues for the past few decades, and the enormous amount of greenhouse gases which are emitting into the atmosphere is leading to this global warming. As a subsequent effect of this global warming, there are a lot of climatic changes are occurring, especially in the polar regions like this, as you can see in these pictures. So, and there are a lot of systematic studies are there. People are working on these aspects, how these climatic changes are occurring, and what are the subsequent effects we are facing on the planet based on this global warming like that. And recently, the group from our University of Edinburgh and Leeds, they analyzed that almost we have lost more than 28 billion tons of ice during the last 3 decades. So it's really in a huge scale. So when you lost this kind of ice from the surface of the earth, then that will give you the subsequent effect like seawater level increasing and the loss of land surfaces. All these things are subsequent effect of this ice rock melting. Okay. So these ice rock meltings are mainly due to this global warming. So that's the main issue. So that's why all the developed countries, the developing countries are meeting yearly once or meeting at the frequent time scale, and they are trying to make some kind of rules and regulations and some kind of protocols for controlling the CO2 emissions. Okay. The CO2 emissions is one of the major reason for this kind of greenhouse effect. And also, please remember, we are also one of the leading CO2 emitters in the world. So if we control the CO2 emissions, then somehow this kind of effect can be controlled, the climatic change and global warming and all. And this is another recent news, which is published in one of the Tamil daily newspapers. And look at that, it's says that the huge size of ice rock melted recently. That is quite even larger than the one which is melted last year. So like that, there are different kind of ice rocks are there at the Antarctic region, and those ice rocks are melting year by year. Okay. And look at the size of this ice rock is almost 3 times higher than the size of the Delhi city. Then just imagine about the impact of this ice melt. Okay. So when you have such kind of huge size of ice rock melting, then the reasonable level of water will increase at the sea surface. Then that leads to a lot of the losses of land surfaces and all other changes in the surface. So these are all the kind of effect of global warming. And this is another data which is also related to the global warming. And this is actually simulated data of our globe, how the temperature is changing as a function of years. So this is simulated by Yokohama Institute of Earth Science in Japan, and they have used some kind of Earth simulated software, and they simulated the temperature variation around the globe as a function of years. And just I have taken 3 snapshots from that video, and just I have shown here. This is as a function of years. The first one is the 1900, and second one is the 2000, and third one is the 2100. Okay. Look at that. The first one, 1900. Almost the globe or around the globe, the white regions are more, right? So the white regions are almost average temperature, which is more comfortable for human lifestyle in the globe. But when there is a red spot, the red spots are hotter regions. And look at the red spot region. The red regions are increasing as a function of years, right? So that shows that average temperature rise as a function of years. So at the interval of 100 years, and the red regions are increasing reasonably from 1900 to 2000, right? When you look at the first 2 images. And look at the third image, that is the future. So that is in 2100. So when you look at that, almost most of the globe becomes red. So that shows the rise of average temperature. If the temperature of the Earth is increasing in this current rate, then the almost all over the world, the average temperature will rise like anything. So the many countries and government and several organizations, they are trying to make a lot of protocols and rules and regulations to control the CO2 emissions, to control the rate of increase of average temperature. Okay. So in that way, somehow we can able to control the rate of global warming. Okay, so this is the kind of scenario what we are facing, and that's mainly due to the modernization of our lifestyle. Okay, and maybe you can look at the slide. There are a lot of industries and automobiles and a lot of incinerators and power plants like that. There are a lot of the technologies are there and the sophistications are there for human lifestyle. All these kind of technologies are emitting a reasonable level of waste heat into the atmosphere. So these waste heats are contain a reasonable amount of greenhouse gases like CO2. So that's why the content of CO2 is quite increasing in the atmosphere, and that leads to the warming. So So, and on the other hand, this is the environmental aspect. And on the other hand, the energy, especially the electric energy. So we need a lot of electric energy, right? So because, for all our daily need, we need electric energy, right? So the electric energy is one of the essential needs for our lifestyle, especially the modern lifestyle. So that means, we are consuming a lot of electric energy. And also the world population is increasing, right? So due to that, the rate of consumption is increasing year by year. But the major way of generating electricity is by burning the fossil fuel, right? But the fossil fuel are not unlimited sources in the planet, right? The fossil fuels are a limited source, and that is going to fully exhaust over the period of time, right? That is one aspect. And another aspect, when you burn that kind of fossil fuel, that also emits a lot of greenhouse gas. That leads to environmental pollution. So instead of burning the fossil fuel, how one can generate the electricity? So that's the way one can solve the problem of environmental pollution and energy demand. And the renewable energy technology. These are all the kind of sustainable technology for fulfilling the energy demand, as well as keep our earth as green as well. So like that, the people are developing and people are working on different aspects of renewable energy technologies like photovoltaic, windmills, biomass, and tidal. Like that, there are a lot of renewable energy technologies out there. So by developing those technologies, we can decrease the dependency of this fossil fuel, and that will help to keep our environment as green as possible, right? So in that series, the thermoelectric is one of the kind of renewable energy technology, and that's the technology. By using that, you can able to control both these environmental issues as well as you can fulfill the energy demand. Because the energies which are coming out, the waste heat from different sources, like this kind of the incinerators and power plants and automobiles, can be converted into the electricity by using this thermal. That means here you can see this is a schematic of a thermoelectric cell, and when you have the heat sources at the junction, then this heat source will help to drive the respective charge carriers in this kind of P-type and N-type thermoelectric material, and that will lead to develop the potential across the system, so that we can able to convert this thermal energy into the electricity. So by this way, we can able to recycle all these kind of waste heat which are coming out from different sources as electricity. So that is why this thermoelectric is a kind of technology. You can use it for controlling the environmental pollution as well as for increasing the energy conversion. Okay, so that is why the people are working on this kind of thermoelectric technology for various problems. Okay, so how we can develop this thermoelectric technology, or what is the current strategy of this thermoelectric technology? Actually, the thermoelectric technology is not so new. This is very old technology, and there are a lot of commercially available thermoelectric modules are there, and also you may heard about this Voyager spacecraft and all other spacecraft. So these spacecrafts are already used this kind of thermoelectric generators, silicon germanium based thermoelectric generators, so that it can able to generate electricity from the heat radiation which are there at the space, and it can convert the electricity.
Excuse
so that
me, sir.
can be useful for. Yes.
Sir, your voice level is low. Your audio is not clear, sir.
Audio is not clear. How about now? Hello.
Now it's okay, sir.
Now it's okay. Okay. So just the mic is a little away from. Okay. So now it's clear, no?
It's okay, sir.
Okay. So shall I start from the here, or shall I continue from here, or I have to start from the previous?
Okay, sir. Continue, sir.
Okay. Fine. So if there is anything, any problems are there, or any voice breakages or any other things, please unmute yourself and please let me know. Okay. Otherwise, I didn't know. Okay, so this thermoelectric technology is already there, for several applications like spacecraft and automobiles like that. So for having such kind of applications, you have to make the thermoelectric device as a module. So for making the thermoelectric device as a module, you can make this kind of thermoelectric licks or thermoelectric pellets of P-type and N-type material, and then you can connect it by using this kind of ceramic paste, and then you can make this kind of arrays of thermoelectric cells. And this is a schematic of such kind of thermoelectric. So once if you have this kind of arrays of thermoelectric cells, then the area of exposure of heat is quite enhanced, so that the most of more amount of heat energy can be radiated, and that can be converted into electricity. So in that way, they are scaling up the technology, and this is a kind of such kind of thermoelectric model. Okay, and this kind of model is already there in the market, and especially in the automobiles. And the automobile people, they used to call it as a catalytic converter. In almost a lot of luxurious cars like Audi and Benz, they are using this technology, and they used to place this kind of catalytic converter in between the engine and the exhaust. And when the exhaust are coming out from the engine, and it can come across this TEG, the catalytic converter, and when it come across through this TEG, then the thermal energy which is coming out from the engine can be converted into electricity, and the rest of the emission can be go out. So due to this kind of technology, there are two beneficial aspects of it. One is that you can convert this part of thermal energy into electricity, and that you can use it for interior purpose of your automobile, like seat warmer or lighting and all. And when the heat energy is converted into electricity, then the resultant emission from the automobile contains less NOx emissions and all other pollutant emissions. So in that aspect, the emission level from the automobile can be reduced with the help of this thermoelectric generators. So that's why the people are preferring to place this TEG in this automobile to control the emission as well as for generating electricity. And like that, there are a lot of thermoelectric modules are available, and these are some of the modules which are available even in online markets. You can buy it for demonstration purpose, and you can connect it to some DC fan, and based on the size, you can have the electricity power. And if you give the thermal energy at opposite end, then if you connect to the DC fan to this electrode, then the fan can run when you have the thermal energy at opposite end. So like that, you can use it for demonstration purpose and all. And this technology can be scaled up, and it can increase the output power by increasing the temperature difference between the hot end and cold end. And that can be done by intentionally introducing some kind of heater at the hot end and cooler at the cold end, so that the temperature difference can be maintained as cheap as possible. Then that cheap temperature gradient will help to drive the thermal power from the hot end to the cold end, so that you can able to increase the output. So like that, the people are trying to scale up the technology for increasing its application. And apart from that, there are a lot of innovative approaches are there for this thermoelectrics, especially after the evolution of nanotechnology. There are a lot of innovations are there, and a lot of modifications are there in thermoelectrics. And one of that is solar thermoelectrics. So not only the thermal energy, not only the waste heat which are coming out from the industries, as well as you can use the solar radiation as a heat source to convert into electricity. So how the solar radiations are converted into the electricity through the photovoltaic, like that you can use the solar radiation as a source of thermal energy to convert into that. But for that, the normal solar radiation may have the temperature of about 40 degrees, right, at the summer region. But that is not quite enough to drive the thermal power. So that to increase the thermal energy, they are doing a lot of modifications, like they are using some kind of optical concentrator, so that the incoming solar radiation can be converged into the hot junction, so that the temperature in the hot junction can be enhanced. And on the opposite end, you can implement some kind of cooling, so that the temperature gradient will be increased and the thermal power can be generated. So like that, we can use some kind of optical concentrator, or we can use some kind of parabolic reflectors, or some kind of optical arrangements to have multiple reflections, and that can be useful to focus the solar incoming solar radiation into the hot junction, and then you can able to maintain the cooling process at the opposite end, so that you can able to increase the gradient, right? So like that, you can use this with the proper optical arrangement. You can use the solar radiation to convert it to using the thermoelectric technology. And like that, the floating solar technology, like you can able to use the solar thermoelectric generator on the sea surface, so that you need not to have separate cooler, but whereas when it floated on the sea surface, or whatever the surface, water surface you may have, then the opposite ends can be effectively cooled. And on the top side, if you have some kind of black body radiation or black body coating, or some kind of optical concentrator, then you can able to increase the temperature at the hot end. So by that way, you can able to have a straight temperature gradient. So the ultimate aim of this thermoelectric technology is that to have a strong temperature gradient. So when you have that kind of strong temperature gradient, and that's the driving force for thermopower generation, and then you can able to have electricity from the system. So this thermoelectric technology is not only useful for electric power generation, as well as you can use this thermoelectric technology for different applications, like thermoelectric power generation, as well as thermoelectric coolers, as well as some kind of thermoelectric based IR detectors, something like that. So because whenever you have some thermal radiation, that may be part of IR radiation, and you'll have some thermopower variation. So by detecting the thermopower variation, you can able to sense whether there is IR radiation or not. So in that aspect, you can use this thermoelectric cell as a IR detector. And when you give electricity, then you can convert. When you give the thermal energy, that can be converted into the electricity. So that is a power conversion mode. And when you give the potential at the pole junction, then based on the Peltier process, Peltier effect, the heat dissipation is structured at opposite. So in by using that, you can able to use this thermoelectric generator as a cooler refrigeration mode. So like that, you can able to use it for different applications. And the functioning of the thermoelectric cell is quite complicated, and it contains a lot of things. So there are a lot of physical properties are there, and you have the p-type and the n-type materials. No, these are all the p-type and the n-type semiconductors. So how the electrons and holes are moving, as well as phonons, how the electron, hole, and phonons are moving in the material, and based on that, all this process will change. So it's quite challenging to improve the power conversion, or to improve the cooling process, or to improve the sensitivity of the photodetector is quite challenging, because all these processes are based on these physical parameters, like the voltage, and how much heat we have applied, and what is the change in the density of the chips, and what is the change in the chemical potential of the material, and what are the changes in the thermal conductivity, and electrical conductivity, and Seebeck coefficient, and mobility of the charge carriers. So all these things are interrelated. So you have to optimize this thermoelectric parameters of each of p-type and n-type material to have the optimum performance. So for that, you have to systematically investigate the electron, hole, and phonon transport in the material. So there are a lot of physics to tune the properties of this material. Then you can able to realize the high performance can be. So as I said, this is not quite easy to achieve the high efficiency like photovoltaic. So say for example, the photovoltaic silicon-based photovoltaic technologies are a kind of the well-matured technology, where you can able to have the high efficiency in the range of about 19%, even for a meter by meter size of solar panels. Okay. But whereas for this thermoelectric technology, the efficiency is not up to the level. So that's the limitations of this technology, and that's why the people are using the different strategies to improve the efficiency. So this is the conversion efficiency of a thermoelectric device, and the conversion efficiency is a function of two factors. One is the ZT. The ZT is nothing but the figure of measure. Let me explain about it in the coming slide. And another one is the temperature gradient. That means the temperature difference between the hot end and cold end. And based on that, the conversion efficiency will be. So look at this is the theoretically calculated conversion efficiency of a thermoelectric device as a function of two parameters. One is the hot end temperature, and another one is the ZT, the figure of merit. So I have shown the different curves for different ZT values, right? And there is one dotted line. I hope you can see. So these dotted lines show the efficiency of a commercial photovoltaic silicon-based solar. Okay, so the efficiency is about 19%. So if you want to have the efficiency of the silicon solar cell, the comparable to the silicon solar cell thermoelectric, then you have to achieve this in two different aspects. One is that you can able to get this efficiency when you increase your hot end temperature up to 1200, right? But if you want to increase your temperature up to 1200, your material should withstand for that, right? But if it not withstand, if the melting point is higher than lower than this one, then it cannot go beyond up to this 1200 Kelvin. But with your ZT is about 1, right? But if your material, the thermal stability is not up to the level, even you can achieve the same conversion efficiency at almost half of this temperature, about 600 Kelvin, right? But in that case, your ZT should be 3 times higher than this one. That means your ZT should be about 3, right? So you can achieve this conversion efficiency either by increasing this hot end temperature or by increasing this ZT. So the hot end temperature is the material parameter, like thermal stability, melting point, and boiling point and all. But the ZT, you can play with ZT by optimizing the thermoelectric characteristics of the material. So how one can optimize? So these are all the the fundamental theoretical relations of this thermoelectric materials. And look at these are the standard relations. One is the figure of merit, as I said in the previous slide. And this is the the ratio between the power factor and thermal conductivity. The kappa is the thermal conductivity, and the S square sigma is the power factor. And here the S is the Seebeck coefficient, and sigma is the electrical conductivity. So S square sigma is the power factor. So when you have this kind of combination, then you can compute the ZT of your material. And the electrical conductivity is a function of carrier density and mobility of the material, right? As a standard relation. And this is another standard mode relation. That means the Seebeck coefficient, how the Seebeck coefficient of the material changes. And the Seebeck coefficient of the material changes based on 2 factors. When all other rest of the parameters are constant. And one is 2 factors. One is the N. N is the carrier concentration. And another one is the M star. M star is the effective mass of the charge carrier. So by tuning this effective mass or carrier density, we can able to tune the Seebeck coefficient of the material. And another one is that kappa. The kappa is the thermal conductivity. So the thermal conductivity contains 2 components. One is the lattice part of thermal conductivity, and another one is the electronic part of thermal conductivity. Okay. So the lattice part of thermal conductivity, the electronic part of thermal conductivity is the function of electrical conductivity according to the Waidmann's law. If there is a change in electrical conductivity, then the electronic part of thermal conductivity will change. But the lattice part of thermal conductivity is not at all related to the electrical conductivity. This is the lattice part of thermal conductivity is independent to the electrical conductivity, but this is a function of TVL. T is the specific heat capacity, and V is the velocity of phonon, and L is the phonon. So these are all the fundamental relations. And if you want to, as I said in the previous slide, if you want to increase the efficiency, you have to increase the ZT, right? So if you want to increase the ZT, you can do by 2 aspects. One is that you can increase the power factor. By increasing the power factor, you can get the high ZT. Or by decreasing the kappa, you can get the high ZT, right? But it's quite challenging because the part of the electrical conductivity is related to part of the thermal conductivity is related to electrical conductivity. So if the electrical conductivities are increasing, the thermal conductivity also will increase. Then the ZT cannot be improved significantly. And look at this is the fundamental relations of all these parameters, sigma, S, and kappa, as a function of carrier concentration for different material like insulators, semiconductors. So this is the optimum range of carrier concentration. If you have the semiconductor with the optimum range of carrier concentration, then you can able to achieve the high power factor compared to all other semiconductor and metallic materials. Okay, so that in that aspect, the people are working on tuning the carrier concentration, on making the material as a heavily doped semiconductor to achieve the high power. And this is the the fundamental relations just to look into the details, the power factor and thermal conductivity, the ratio between these two is a figure of merit, and this is a strategy. So if you want to increase the ZT, either you have to increase the power factor or you have to control the lattice part of thermal conductivity. Because the kappa E cannot be controlled because the kappa E is related to sigma according to the Bierman transfer. But this is valid only for metallic material, for high carrier density material. But whereas in semiconductor, this kappa L is quite dominant than the kappa E. So that the semiconducting materials are the appropriate material system to dependently control the electron transport and quantum. So that is why the people are working on different kind of semiconductors to design a new kind of thermoelectric material with high performance. And these are some of the several strategies people are following to improve the efficiency of thermoelectric materials, like defect engineering. So that means you have to have some kind of intentionally introduced defects or some kind of inherent defects in the material, or you have to tune the defect density in the material by using different strategies. Like you can make this kind of grain boundaries, and you can introduce this kind of alloying, and you can introduce this kind of nano inclusions, and you can introduce this kind of point defects. So like that, you have to have a lot of defects. So, and another important the beauty of science is that the defects up to the reasonable level of defects are quite beneficial for improving your performance. And this is completely contradictory to the semiconductor physics, like microelectronics, because for IC fabrication you can have the silicon, but the silicon should be extremely high quality, and there should not be any macro size defects. So the defects are highly harmful for almost all the electronic properties of the material. So because these kind of defects will act as a kind of recombination center to trap the carrier and kill the performance. So that's why the people are always doing some kind of defect engineering to control the defect to improve the performance. But this is quite opposite. In thermoelectrics, you need to have some kind of defects and up to some reasonable level. So these defects are helping to improve the performance. How? Let's see here. So as I said, this is the Weidmann-Franz law, so that the part of the electronic thermal conductivity is related to electrical conductivity. But whereas the semiconductor, the kappa L is dominant, that is lattice part of thermal conductivity is dominant, right? And how one can control the lattice part of thermal conductivity, that is important. So if you control the lattice part of thermal conductivity, then the total thermal conductivity can be controlled, and that will lead to increase the safety. And how we can do that? So this is the relation that is shown in the previous slide, and this is the relation that is the CVL. The C and V are based on the material, that is phonon velocity and the phonon capacity. But whereas this L is a phonon mean free path. So this phonon mean free path can be tuned by defect engineering. So if you have these kind of defects like grain boundaries or alloys or this kind of inclusions at the grain boundary, inclusions at the grind. So these kind of the defects act as a phonon scattering center. So when you have these defects, then the phonon scattering will be increased. So when the phonon scatterings are increased, the phonon mean free path gets decreased. So when the phonon mean free path gets decreased, the lattice part of thermoconductivity will be decreased, and that will lead to improved detect. So that is the strategy. That means if you have the defects, and these defects are acting as a phonon scattering center, and they effectively scatter the phonon, and due to that, the lattice phonon mean free path gets decreased, and that leads to low kappa L, and which will result high ZT. In that aspect, the reasonable amount of defects are quite beneficial for improving the ZT. And these are some of the novel approaches that people are following to improve the thermoelectric performance of the material. Like one is that reducing the thermal conductivity without degrading the electrical conductivity. That is the first strategy, and how one can able to control the thermal conductivity without affecting the electrical conductivity. And that can be done by effectively controlling the lattice part of thermal conductivity using this kind of nano inclusion, CFS, and quantum chapter. And another one is that the nanostructuring of the material. So this is another aspect. So when you have nanostructured material, then that will have a lot of the variations in the DOIS due to the confinement process. And when you have that variation in the DOIS, and that will change the effective mass of the material, and the SPECTROPHYSICS coefficient can be enhanced without affecting the conductor. Or almost we can make the alpha SPECTROPHYSICS coefficient and electrical conductivity as independent parameter to tune by using the nanostructure. And also you can able to reduce the kappa by making a lot of interfaces like in the nanostructure. And another one is the energy filtering effect. When you make this kind of multiple interfaces with the different gain boundary energy, then the carrier filtering is possible so that the carrier selectivity will be there for transport, and that will lead to increase the SPECTROPHYSICS coefficient and the ZT. So the ultimate aim of the thermoelectric researchers is to find a kind of material like phonon glass electron crystal. So that means you should have a material which should have the characteristics like it should have the electron transport as like in crystal and phonon transport as like in glass. That's it. If you have such kind of material, and that will have high flux. So this is another example of nanostructuring, how the nanostructuring helps for improving the thermoelectric performance. And look at that. This is the example of DOIS variation on the 3D and 2D material. In the 3D, it's quite continuous, whereas in the 2D material, it's quite confined in one direction, and it's relatively free in another two directions, so that the density of states are confined in certain energy level compared to the other energy level. And due to this kind of variation, the density of states, and look at the effective mass. The effective mass is a function of density of state. And if you confine the density of state at certain energy level, and there the effective mass can be enhanced, and that will lead to improve the SPECTROPHYSICS coefficient according to the Moore relation. So that's why if you have the 2D confinement or 1D confinement, and that will have a subsequent change in the DOIS, and that will lead to improve the SPECTROPHYSICS coefficient. These are some of the examples of computer results, like if you have the 2D confinement in different directions, like X is the plane, Y is the plane of this well-known bismuth telluride sample, and if you have certain confinement in certain direction, and that is when you reduce the confinement scale, and there is a huge increase in the safety along certain plane, and when you reduce the well thickness, quantum well thickness. Right, and like that, the carrier power factor also can be enhanced when you reduce the quantum well from 5 nanometer to the 1.5 nanometer, and that's also mainly based on changes in the effective mass, and that leads to change in the S and then the overall stack. So like that, there are a lot of strategies are there people are following to improve the performance, and the ultimate aim of thermoelectric researchers is to find this kind of phonon glass electron crystals. And mainly this kind of the high TC superconductors and the high entropy alloys and some kind of highly complicated layered structures are quite useful for realizing this kind of phonon glass electron crystals. So when you have this kind of high entropy, high complexity in the structure, and that leads to high entropy level, and that leads to increase the phonon scattering. And when you have the ordered layers on the surface, and that leads to enhance electron transport, so that you can able to realize that phonon glass electron crystal by using this kind of highly complicated. And these are all some of the the reported results of nanostructuring, how the nanostructurings are beneficial. And look at that, in two different systems, they have realized really significant improvement in the ZT when they nanostructure the material compared to the bulk. There are the ZT is reasonably increased in this system as well as in this system, and that's mainly due to the significant reduction in thermal conductivity of the system, and that kind of significant reduction of thermal conductivity is mainly due to the phonon scattering at the interface. Okay, so like that, there are different kind of thermoelectric materials are there, and these are all some of the materials reported in the literatures. And silicon germanium is one and only material which can withstand even more than 1000 Kelvin. And almost all the reported semiconducting materials are having the thermal stability less than 1000 Kelvin, although they have high performance, like zinc antimonide and cobalt antimonide and bismuth telluride. These are low temperature materials. So like that, there are different kinds of semiconductor materials are there. Some of them are commercially available, and some of them are still in R&D. And to have the high performance in the thermoelectric material, your ZT should be greater than or equal to 1, and so that the people are trying to improve the ZT by following the different strategies, like as I have shown in the previous slide. Okay, and when you come to the oxide semiconductor, these are all almost most of them are semiconductor-based materials. And to process all the semiconductor-based material, you need to have some kind of specialized atmosphere and controlled atmosphere with dust-free conditions. And it's not so easy to process at the open atmosphere due to the oxidation process. But whereas the oxide materials are quite stable against the open atmosphere, as well as another important thing is that the thermal stability. Look at that, the thermal stability is almost for most of the materials are less than 1000 Kelvin, except silicon germanium. Whereas here, almost many of the materials are showing high performance even after 1000 Kelvin. But look at the y-axis. The ZT, the performance is quite high for semiconductor material, but whereas for oxide, the performance is not up to the level. But still, the temperature stabilities are more. So if you improve the ZT even more than 1, then you can able to use this kind of oxide thermoelectric materials for high temperature applications. So with this motive, the people are working on different kind of oxide semiconductors, and we also working on different kind of oxide semiconductors. I'll show some of our results, and then I'll continue. Okay, so these are all, this is the first study about the cobalt oxide. This is one of the oxide semiconductor, and we just did some systematic investigation on the impact of bismuth substitution at the cobalt site and how these bismuth substitutions are helping to improve the thermoelectric performance of cobalt oxide. This is a protocol which we followed for synthesizing these cobalt oxide nanostructures. And after that, we studied by SADI and SEM and EDS and thermoelectric analysis to analyze the structural, morphological, and thermoelectric characteristics. And this is the structural features of the sample, and this is the exact importance. And look at that, there is a systematic change in the phases of the material. This is the pure sample, the cobalt oxide sample, and in the pure sample, there are the different phases are there. Almost when the bismuth content is substituted at 2.5%, then there is cobalt oxide phases are there with the three different phases like the CO3O4 and CO2O2 and COO. And when the bismuth content increases, then the phase purity occurs. So what is a 10% bismuth substituted sample? Almost the cobalt substituted sample, bismuth substituted sample shows a complete dissolution of bismuth. And when the bismuth content increases about 20%, there is a secondary phase formation are there, like the bismuth oxide is also formed, and that's mainly due to the variation in the solid solubility limit of the bismuth substitution in the cobalt oxide lattice. And this is the same images, and the same images show the spherical morphology of almost all the samples, and the samples are quite agglomerated. The sizes are almost less than 100 nanometers. And this is the ISPA analysis of the bismuth substituted cobalt oxide. And look at that, the cobalt is there and bismuth is there and the oxygen is there. That means that shows the presence of bismuth incorporation in the cobalt oxide lattice. And we have the synelectron splitting energy for cobalt 50, that's about 14.9, that is less than 15 electron volt. And that shows the mixed valence of cobalt in the sample, and that leads to mixed phases in the substituted sample. And this is the pelletized nanostructured powder, and we have prepared the powder and we have pelletized it as a circular sample, and we have used it for electron transport by thermoelectric characteristics. So like this is the electrical resistivity of the pelletized nanostructured bismuth substituted cobalt oxide, and the pure sample, the bismuth free sample shows relatively high resistivity, and when the bismuth is substituted at the cobalt side, the resistivity is drastically decreases as a function of bismuth content, and almost for all the samples the resistivity decreases as a function of that shows the the semiconductor behavior of the sample. And why the resistivity is decreasing, and that's because of the variation in the carrier density. And look at that the carrier concentrations are increasing as a function of bismuth content. Up to 2 order increase is there, and slightly decreased at high bismuth content. That's due to the formation of secondary phases in the sample, and due to that the low resistivity has been observed, and the SIBO coefficient has been measured for this pelletized nanostructure by placing the sample between the hot end and cold end. And the SIBO coefficient is also increased as a function of bismuth content, and 20% bismuth extruded sample shows high SIBO coefficient compared to the two samples. And by using that, measured resistivity and SIBO coefficient, the power factor has been calculated. As I have shown in the beginning of the slide, the power factor is S squared sigma, so that from the measured S square and rho, they can able to calculate the power factor. And the power factor is also quite enhanced compared to the bismuth alone substitute, bismuth free sample. So the bismuth substitution is quite beneficial for successfully enhancing the power factor of this kind of oxide semiconductors. And like that, we are also working on this zinc cobaltate nanostructure, and this is one of the rarely studied semiconductor material. And the impact of bismuth substitution at the cobalt site is studied in the semiconductor, and the protocol is quite similar of the previous system. And this is a pelletized nanostructured sample, and circular thermoelectric legs have been fabricated, and you can use such kind of thermoelectric legs for thermoelectric device fabrication. So this is the the kind of XR departments of zinc cobalt oxide, bismuth substituted zinc cobalt oxide, and look at that the Q phase is assigned at the Q sample, and when the bismuth substitutions are there, the bismuth is completely dissolved up to 10% of bismuth, and when the bismuth content increases beyond 10%, there are secondary phases are there like bismuth oxide, and that's mainly due to the exceeding the solid solubility limit, and the alloying effect is also there up to the 10% of bismuth, and there is a systematic variation in the lattice parameter due to the substitution of bismuth at the cobalt site. And the morphological variations are also clearly observed in the sample, like from the spherical to the sheet-like morphology. That means, the presence of bismuth in the cobalt oxide, zinc cobalt oxide changes the growth kinetics in the sample, so that the growth structures have been changed from the spherical to the sheet-like structure. And the same thing has been retained when you make it as a pellet and sintered high temperature. This is the spherical morphology of the surface of the pelletized thermoelectric legs, and the sheet-like structures are observed in the heavily bismuth substituted sample. And another thing is that this is the the heavily bismuth substituted sample, the EDX mapping. And the EDX mapping, we observed the important information like the white precipitate. So these white precipitates are here, and when you look at the compositional analysis at the white precipitate, almost that is rich of oxygen and bismuth. So that means the bismuth oxygen, bismuth oxide secondary phases are there, and these kind of bismuth oxide secondary phases may precipitated on the surface, or that may be also presented as secondary phase in the sample, and that has been detected by using this EDX mapping along with all other rest of the elements which are distributed in the sample, and which is supportive for this analysis. And the carrier density concentration has been measured as a function of bismuth content, and when the bismuth content increases, the carrier density has been increased, and slightly decreases at the heavily bismuth substituted sample, and that's due to secondary phase formation. And the resistivity to that, the resistivity is decreased for the bismuth substituted sample. Look at that. So that's due to the variation in the carrier density. So these are all the high carrier density materials. So the carrier resistivity of the low carrier density is the 20% bismuth substituted sample. So all this shows that the semiconducting behavior of the sample and the complete dissolution of bismuth in the zinc cobalt oxide sample. And again, the SIBO coefficient has been decreased as a function of the bismuth content, and the sample at 10% bismuth substituted sample shows very low SIBO coefficient compared to the two sample, and for the 20% bismuth substituted sample, the SIBO coefficient is slightly improved due to its high resistive nature. And the power factor has been calculated from the measured Seebeck coefficient and electrical resistivity. And the 10% business substituted sample shows a relatively high power factor compared to the rest of the samples. And we have measured the thermal conductivity of that 10% business substituted sample and pure zinc cobalt oxide. And the thermal conductivity is slightly decreased for business substituted sample, especially at high temperature region. And from the measured the thermal conductivity and the Seebeck coefficient power factor, the ZT has been calculated. The ZT has been reasonably improved for the business substituted sample compared to the business free sample. So that means the business substitution, the zinc cobalt oxide is a promising approach for improving the ZT. So although the observed ZT is not so high compared to the semiconductor material, but there is a positive sign of improvement in the ZT. So further, optimization and R&D is needed for increasing the ZT of this kind of oxide-based material. And like that, we are also working on different kind of material like copper manganese oxide. That is one of the other nanostructure rarely studied oxide semiconductor, and where we just studied the effect of the ISPA substitution at the copper manganese oxide nanostructure and studied the characteristics. The sample by ball milling, and then we made it as a powder and pelletized as a nanostructured pellets and used for thermoelectric characteristics. And this is the structural features of that ytterbium substituted copper manganese oxide, and that shows the the complete dissolution of bismuth in the ytterbium in the lattice. But especially at a high content, there is a secondary phase formations are there, and that's due to the ytterbium oxide, and that's due to the excess solid solubility limit of the ytterbium. And this is the same and the compositional mapping of the copper manganese oxide with the yttrium substitution. And almost it shows the distribution of all these elements present in the samples, and especially the yttriums are presented at the sample. It shows the incorporation of the yttrium in the sample. And the sample has been pelletized and measured the resistivity, Seebeck coefficient, and power factor. And the resistivity has been decreased as a function of temperature, which shows the semiconductor behavior. And compared to the two samples, the resistivity is slightly decreased for Y1 and Y2 sample, and slightly increased for Y3 sample due to the secondary phase formation. And the Seebeck coefficient also decreased for Y1, Y2 sample compared to the pure one, and slightly increased for high substituted sample. And based on the measured resistivity and Seebeck coefficient, the power factor has been calculated, and the power factor is relatively high, almost in the order of milliwatts for yttrium substituted sample. And the yttrium 5% yttrium substituted sample shows relatively high power factor compared to the other samples. And the thermal conductivity has been measured for these samples, and look at that. This is the thermal conductivity of the two samples, and these are the thermal conductivity of the yttrium substituted sample. When the yttrium substitute at the manganese site of the TMO, there is a drastic reduction in the thermal conductivity, and the lattice thermal conductivity and electronic thermal conductivity has been retrieved from this thermal conductivity, and the which shows that the drastic reduction in the lattice thermal conductivity for the Y1 sample, and that's mainly due to the substitution of yttrium at the manganese, because the yttrium is a large ionic radius sample, so that the unharmonics in the bonding will increase, and that leads to improve the phonon scattering, so that will effectively decrease the lattice part of thermal conductivity. And due to that extremely low thermal conductivity, the ZT of the sample has been increased recently at the for TMO Y1 sample, and that's mainly due to the complete dissolution of yttrium, and that leads to increase the harmonics in the bonding, so that the low thermal conductivity has been observed, that resulted high ZT of the material. So yeah, like that, we are working on different kind of oxide semiconductor apart from these, and zinc oxide and copper oxide and like that, and semiconducting material like tin selenide and zinc selenide, kind of silicon germanium. Like that, we are working on different kind of oxide semiconductors, and there are several strategies are there to improve their performance, and we are also following some of them. to improve the high performance of the material. So like that, I just summarized my talk, and we have systematically studied the impact of physical substitution on the thermoelectric characteristics of the cobalt oxide and the zinc cobalt oxide. And we observed this is significant improvement in the power factor and ZT of the oxide semiconductors by substituting the differs at the respective samples, and like that, you can able to follow different strategies to improve their improve the thermoelectric performance of different kind of oxygen. So I'd like to thank the funding agencies with their supporters for our research, like DST and KMRT Japan, Rope University Japan, for the support research. Thank you. So I'll stop here. So if you have any comments or questions.
Thank you, sir, for a nice presentation. Dear participants, do you have any doubt or any clarification? You can ask. Sir, one participant asked the questions in the chat box, sir.
Yes, sir.
Do you use any binder for pelletizing?
No, sir. We have not used any binder because almost all the oxide semiconductors are pelletized at high pressure with hydraulic pressing, as well as by SPS fast plasma sintering also we have used to pelletize the sample at high pressure and high temperature. So no need of binder. And sometimes if the adherence is not so good, we can use the binder, but we have to be very careful whether during the post pelletizing, during the sintering, all the binding materials are removed or not. Otherwise, it may affect the electron transfer. But people are using some binder. But in our case, we have not.
Any questions from the participants?
Yeah, some I think the chat box. Yeah, the 2D material will increase ZT. Yes, of course, you are right. When you have the 2D material, and definitely, you can able to have the high performance because of the confinement as well as the 2D structure. And when you have the stacking of 2D structure, as I shown in the boron glass electron system, the high TC superconductor or layered semiconductors or layered oxide materials. So these are all example of those kind of complex structures. So when you have that kind of complex structures with the high ordering on a certain direction, then you can able to realize the high performance in the material. That is one thing. And another one asked kindly let me know let us know the role of polymeric composite material in improving the thermal energy. Of course, nowadays the people are using some polymer-based materials as well as some kind of conducting polymer-based materials for flexible thermoelectrics. So flexible thermoelectrics, they are using this kind of conducting polymers, and organic materials also they are using for thermoelectric applications. And there are a lot of innovations nowadays taking place, and they are trying to modify the system, and they are using different combinations of systems to improve their performance. And not only the performance, as well as to increase the widening of the applications, they are making this kind of wearable thermoelectrics and flexible thermoelectrics, and micro size portable thermoelectrics. So like that, they are using different kind of modifications and different kind of material combinations they are using to improve their performance. So of course, the polymer composite is also helping for improving the performance. And how to determine the effective mass by experiment, Srinivasan asked to everyone. is there any oxygen deficiencies observed? Yeah, of course, both are very important questions. But effective mass, we have not measured actually, and the effective mass we have taken from the literature, and we have used the fitting process to estimate the effective mass, density of states effective mass, based on the density of states, and we can fit the variation of the Lorentz number and density of states by using from the Tibo coefficient and carrier concentration value, and by the fitting of all this data in using some software, they are computing the effective mass of the system, and it's a relative effective mass, and that can be computed by using some software, using the experimentally by feeding the experimentally measured Tibo coefficient and carrier transport property. And another one is, of course, we observe the oxygen deficiency in the sample. One of the system like calcium cobalt oxide, we have used the calcium cobalt, we have studied the calcium cobalt oxide. There we observe the oxygen deficient phase, and this oxygen deficiency has been controlled by substituting the heterovalent substitution, and that's also we confirmed by X-phase analysis. So initially it was oxygen deficient phase, and the oxygen deficiency was decreased by increasing the oxygen content by substituting the heterovalent material, so that the conductivity has been improved in the sample by changing the oxygen vacancy in the oxide sample. But that is an unpublished one, so that's why I didn't show here. But we observed the oxygen deficient phases as well in this kind of oxide material.
Sir, is there any 2D oxide materials?
There are a lot of 2D oxide materials are there, and people are working on different kind of 2D oxide materials are there, like zinc selenide. They are making it as a 2D material, and tin telluride also, as well as this kind of antimonane and bismuthane. These are all the 2D material, and they are trying to use for and of course graphene based. Recently we also used this graphene to make a composite with the STO, and it shows the high performance compared to the pure STO, and like that there are a lot of 2D materials are there, and we can use that to combine to make it as a composite, or we can study it alone as well. There are a lot of 2D materials are coming out.
Yeah, I am asking oxide materials, sir, 2D oxide material. Since I am working with bismuth telluride 2D material. Okay. Is there any 2D oxide materials? Because since more stable with temperature, oxide materials.
Yeah. But the exfoliation of this 2D material, oxide 2D material is not easy, but oxide layered materials are there, like sodium cobalt oxide, calcium cobalt oxide, oxide layered material. But making as a 2D, I'm not sure. I cannot remember any oxide 2D material. I don't know.
So do you have characterization for CPEC and thermal conductivity for 2D material? Or you are having only bulk material facility?
Yeah, we have. That means, we have a facility for measuring the thin film.
Yeah. Okay, if so, I will contact you, sir.
Okay, sure.
I am from PSG Tech, Sudarshan.
Okay, sir. Okay.
Any more question? Okay, sir. Thank you, sir. We come to the end of the session. It is a time for formal order. Yes, sir.
Sir, okay. Please finish the vote of thanks, and tell you what. Maybe Professor Jamal joined at the time. Suppose if it is delayed because he is in another meeting, he will join at the time. Suppose if it is delayed, please wait for 5 to 10 minutes. Okay, he will join for the next session. Okay, you can proceed as per your schedule.
I take this opportunity to propose vote of thanks for this session. I would like to thank our resource person, Dr. M. Arivanandan, Professor, Center for Nanoscience and Technology, Anna University, Chennai, for delivering a wonderful lecture on oxide thermoelectric materials for energy harvesting. He explained the detailed information about thermoelectric materials. Okay, it was very useful and more informative, sir. Thank you, sir, for your nice presentation. So next, I would like to thank our head of the department, Dr. M. Jamal Jafar, sir, who has given constant encouragement and invaluable support in organizing this two-day faculty development program. So next, I would like to thank the faculty members and the supporting staff of our department for their constant support and help for the conduct of this two-day FDB program. So finally, I thank all the participants for their active participation and patient hearing. Thank you, all of you.
Thank you, sir. Thank you for the session. Thank you.
Dear participants, next we move to session 2.
Good morning, dear participants. It is the good morning from Jamal Mohamed College Department of Physics. Arivanandan sir, he has given a glimpse of that information. And of course, the next session starts by only 11:30 because Jamal sir, he is busy with the Voters Day program. He is busy with that, and by 11:30 only he can come and join. Just before that, just we want to have some information to be shared among yourself. That is, we are having DBT Star College scheme. Actually, the maximum participants are from teaching side only. Excuse me. Mute.
Yeah, dear participants, okay, actually, according to the schedule, we have extra time. So I would like to share some other topic like semiconductor-based thermoelectrics. So let me share the slide and I'll talk about the silicon germanium-based thermoelectrics for another 30 to 40 minutes, and then Professor Jamal will take over the session. Okay. So please be patient and be in online, and please don't move from this session. Okay, so let me share the slides about this nanostructure, the semiconductor-based thermoelectrics, and okay. Please wait. Okay, so as I said, in the beginning of the talk, we are also working on silicon germanium and indium gallium antimony based thermoelectric material for energy harvesting. And just I would like to share some of our results on indium gallium antimony and silicon germanium based samples. And these are all, I hope, it's quite interesting. And anything, if you want to ask anything also, you can stop me even in the middle of the talk and we can, okay, that's not an issue. And I hope you can see the slides now, okay? Can you see it? Right,
Yes, sir.
hello? Yeah.
Yes, sir.
So
Visible, sir.
Okay, thank you. So this is, another kind of alloy semiconductor. This is a ternary alloy semiconductor. That means gallium antimony is the base one, and in the gallium antimony we just substituted indium at the gallium side with a different composition. Then we have prepared the indium gallium antimony at the whole composition window, like from the gallium antimony side to the indium antimony side, and the indium rich indium gallium antimony and gallium rich indium gallium antimony, like that. And these are all the kind of polycrystalline samples. We just taken the source material and we just melted it and cooled it. So melt and crystallization process, and that's why, due to the this is the same image of that indium gallium antimony sample, and this is a semiconductor sample, and you cannot melt it at openness mask here. So you have to melt it at vacuum or inverted mass here or reduction mass here. Actually, we use the hydrogen ambient to process this ternary alloy semiconductor, and we just melted it at the respective melting temperature, because the melting temperature may change based on the composition of the alloy, and because that will be in between the gallium antimony and indium antimony, and based on the composition we just fixed the growth temperature, and we just melted it at a high temperature and cooled at the predetermined cooling rate, and we observed the polycrystalline, we got the polycrystalline sample, and these are the surface structure of the sample. And look at the EDX mapping of that indium gallium nitride. And there are some kind of the island growths are there, right? Hello, yes sir.
No, sir, you can
Hello?
continue, sir. Oh, okay, sir.
Okay, okay. So look at this image. There are a lot of the island kind of inhomogeneities are there, and that's mainly due to the segregation variations between the indium in the gallium antimony system, and the indium is relatively larger than gallium, and then when it substitute when it incorporates into gallium antimony lattice, there is some kind of segregation lagging will be there, and due to that the compositional inhomogeneities are there, and we have found the oxygen is quite homogeneous, antimony is quite homogeneous compared to the indium and the gallium, and we observed the presence of both indium gallium antimony, and we use these indium gallium antimony at a different composition as a material to analyze their thermoelectric characteristics as a function of indium composition. And this is the Raman spectra of that indium gallium antimony. Okay, and look at the Raman spectra. The pure the Raman spectra of pure indium antimony is here, and the Raman spectra of pure gallium antimony is at the bottom, indium antimony is at the top, right? And in between, this is the alloy, ternary alloy, as a function of indium composition. Okay, so the in the pure gallium antimony, the TO and the LO modes are dominant. That means the optical modes are dominant in the pure gallium antimony. Whereas in the alloy system, there are the acoustic antimony related acoustic modes are dominant. Okay, so that means the optic modes of phonons are quite suppressed, and the acoustic mode of antimony related peaks are dominant in the ternary alloy. So, and in the both binary sample like indium antimony, gallium antimony, the optic mode of phonons are quite dominant, whereas in the alloy, the acoustic mode of phonons are dominant. So this is the kind of very valid information for in terms of thermoelectric, because I forgot to show that kind of slides in the previous session. Actually, this is a kind of that session. That means that information. That means how the phonons are moving, because the thermal conductivity is an important factor in the thermoelectric characteristics, and one has to control the thermal conductivity. And the thermal conductivity or the thermal transport occurs in the material through the phonon vibration, right? Then the phonon vibration, there are two modes of phonon vibration. One is acoustic mode and another one is the optic mode, right? So this acoustic mode, the phonon vibrations are in phase with the nearest neighbors. So that's the one important variation. Whereas in the optic mode, the phases are anti-phase. The neighbors are in anti-phase. So that the net transport in the optic mode of transport is quite low compared to the in-phase acoustic mode. So that means the acoustic mode of phonons are dominant, means the thermal transport will be quite high. When the optic transports are dominant, then the thermal transport is quite low due to the anti-phase nature. So like that, there are different kind of mode of transport, like in silicon germanium, these four. One is the transverse optic and longitudinal optic, and the transverse acoustic and longitudinal acoustic, right? So here that kind of variations are there in ternary and binary alloys, and there is a variation in the mode of vibration, and that is going to affect the thermoelectric characteristics of the material. And this is the surface morphological image of the etched surface of the sample, that is indium antimony, gallium antimony, and indium gallium antimony. Okay, and there are circular elliptical shape edge patterns are there, edge pits are there, and these edge pits are changed for different as a function of composition. And by counting these edge pits, the edge pit densities are being calculated, and these edge pit densities are in the range of 10 to the power of 6 per cm square. So that means all these alloy semiconductors are having the reasonable level of HP density. So that means they are polycrystalline nature, polycrystalline samples. Obviously, this is quite reasonable range of EPDs in these alloy semiconductors. And then with that, we measured the resistivity and the Sieber coefficient of this ternary alloy semiconductor as a binary semiconductor. And look at that, this is the semiconductor resistivity variation as a function of temperature for indium antimony, gallium antimony, and the indium gallium antimony. And for the indium gallium antimony, the resistivity is decreasing as a function of temperature, shows the semiconducting behavior. And this is quite metallic in nature for the gallium antimony alone. And whereas for indium antimony also it shows the semiconducting behavior. And the Sieber coefficient of gallium antimony shows the positive value, especially and also the values are quite high, and that's mainly due to the p-type nature of the sample. But whereas when the indium is substituted in the gallium antimony, the sample becomes n-type, and the resistivities or the Sieber coefficient are relatively low, and that's in the order of -200 to 400. So that shows that the variation, the variation in the Sieber coefficient, and each the values are changing based on the resistivity in the sample according to the mode relation. And this is the thermoelectric properties of that alloy semiconductors. That means in the measured Sieber coefficient and the electrical resistivity, the power factor has been calculated. And look at that, the power factor is quite high for indium antimony, and that's mainly due to the narrow bandgap, because the indium antimony is a narrow bandgap semiconductor compared to the gallium antimony. And due to the narrow bandgap semiconductor, the resistivity is extremely low, so that the conductivity is extremely high. And due to the high conductivity, the power factor is enormously improved compared to the indium gallium antimony. But when you compare the ternary alloy, so among the ternary alloy, this 80% indium substituted sample shows relatively high power factor compared to the rest of the ternary alloy. And this is the thermal conductivity. So look at the thermal conductivity. The thermal conductivity is quite high for gallium antimony. Wide bandgap, that is relatively bandgap is quite high. And of course, the indium antimony as well shows high thermal conductivity, because these are all the binary semiconductors. Whereas when you have the alloy, the ternary alloy, the thermal conductivity has been drastically decreased compared to the binary sample due to the variation in the lattice mismatch between the indium and the antimony. And the lattice is quite strained in the indium gallium antimony compared to the indium antimony and gallium antimony. And when you have that kind of enharmonicity in the ternary alloy, then the phonon scattering will be high, as it is reflected here. And look at that. This is the thermal lattice part of thermal conductivity, and the lattice part of thermal conductivity is also quite high for binary sample like gallium antimony and indium antimony. And whereas this is very low for ternary alloy. That means the ternary alloy, there is indium substitution in the gallium antimony, and the lattice is quite strained compared to the gallium antimony and indium antimony. And due to that lattice strain and the bond and unharmonicity will be there, and that effectively scatters the phonon, so that the lattice thermal conductivity is quite high. So this is quite beneficial for improving the thermoelectric characteristics, as we have seen in the previous session. So when you have this kind of extremely low lattice thermal conductivity, the overall performance can be enhanced, and that reflected here. And this is the indium antimony shows relatively high ZT, and that's mainly due to the narrow bandgap semiconductor that results extremely high carrier density and conductivity. But whereas when you look at the ternary alloy, then there is a systematic improvement in the ZT, right? The 80% indium and 20% gallium antimony alloy shows relatively high figure of merit compared to the other ternary alloy. So that means this ternary alloy shows the possibility of tuning the thermoelectric characteristics, especially you can able to control the lattice part of thermal conductivity like this. And when you have the low lattice thermal conductivity, and you can able to how the lattice thermal conductivity is effectively decreased. One is that the lattice strain, and another one is that the acoustic mode of phonon. Acoustic mode of phonon, the in-phase vibration of acoustic mode of phonon are effectively scattered. But the acoustic mode of phonons are dominant in this on the ternary alloy, but these acoustic mode of phonons are effectively scattered by the point effect in the sample, as schematically shown here in the form of pitch. There are a lot of point effects out there. So these point defects are effectively scatter the acoustic mode of phonons, and due to the effective scattering of acoustic phonon, the lattice thermal conductivities are drastically decreased, and due to that, the figure of merit has been increased, especially in the ternary alloy sample. So like that, if you by making the alloy, you can able to suppress certain mode of phonon vibration, and by having the certain mode of phonon vibration, and you can able to control the thermal transfer. And by creating the defects in the sample, you can able to increase the phonon scattering centers, and that scattering centers effectively scatter the phonon, and that will use to control the lattice part of thermal conductivity, and that leads to high performance. So this shows that there is a feasibility of further improving the thermoelectric characteristics of this ternary alloy semiconductors, and that will lead to that is quite possible, and such kind of R&D is also under process. Okay, and that is another one is that the silicon germanium. The silicon germanium is another one of the important alloy semiconductors, as I have shown in the beginning of this talk. So the silicon germanium is a kind of the alloy, fully miscible alloy semiconductor, and the melting point of silicon is higher and germanium is low, so that you can able to have this kind of completely miscible silicon germanium alloy at the full composition ratio. And this kind of silicon germanium can be prepared by different methods, like the Caesar method or melt and quenching method or vertical gradient fusion method, something like that. But the problem with that kind of technology is that the compositional variation. There is a wide variations in there. I don't have that slide, but anyway, the band gap, the phase diagram of the silicon germanium, and there is a wide gap between the silicon and germanium. And due to that wide gap, there is a drastic variation in the composition of the resultant silicon germanium. And when you have such kind of drastic variation in the grown silicon germanium, then their respective thermoelectric characteristics also will change as a function of germanium composition. So in order to avoid that drastic variation in the thermoelectric characteristics, the people have tried to grow compositionally homogeneous silicon germanium. So when you have such kind of compositionally homogeneous silicon germanium, then you can have the consistent properties of the sample throughout the ingot. Okay, so that you need a compositionally homogeneous silicon germanium to realize the consistent performance throughout the sample. So for that, there are different strategies there, and we have implemented some kind of the mild temperature gradient process. So this is a vertical gradient furnace which we have used, and it contains 3 zones which are independently controlled by the thermocouple, and the zone temperature can be controlled, and by modifying the zone temperature, you can able to control the thermal gradient across the sample, and by measuring the thermal profile, you can able to fix the position of the silicon germanium sample at appropriate places, so that then you can conduct the experiment. And this is the thermal cycle which we follow for growing silicon germanium at the 50-50 composition, because the growth temperature we fix at 1100, and that is optimum for 50-50 composition. And this is the gradient which we implemented. This is the temperature profile in the furnace, and we just implemented the temperature difference between the seed interface and feed interface around 1124 to 1130. So that is the temperature difference between the seed interface and feed interface is quite low. So that means the temperature gradient is also quite low. So that is 0.4 degrees Celsius. So this is extremely low temperature gradient. And when you conduct the growth experiment at this extremely low temperature gradient, then you can able to arrest the temperature fluctuation at the growth interface, because once the crystal is grown along this growth interface, then the interface position will improve from the cold end to the cold temperature to the hot temperature. So that means when the growth interface is moving towards the top, then the temperature of the growth interface also will increase. Then the composition fluctuation will be there. Suppose if you apply this mild temperature gradient, then the temperature fluctuation along the growth interface may be suppressed, and that will result highly compositionally homogeneous silicon germanium. And that's what we did here. This is the sample before the experiment, and this is the sample after the experiment. And look at that. This is a cross-section view of the sample. So this is the dotted lines shows the region where the composition is measured along the radial direction, and the solid line shows the region where the composition is measured along the growth direction. And these are all the data. When you look at the data, so the data are quite quite homogeneous, both along the growth direction and radial direction. And this is the composition gradient. So the composition gradient is extremely low, almost it's in the order of 2 × 10⁻³ per mm, right? So that kind of extremely low composition fluctuation has been obtained, and that shows the composition homogeneity in the sample, both in radial as well as along the growth direction. And this is measured exactly at the interface and about 6 mm after the interface. And almost in both the regions, the composition is quite homogeneous. So if you have such kind of compositionally homogeneous silicon germanium, then you can able to observe the thermoelectric performance, almost same thermoelectric performance throughout the grown sample. And that's the beneficial aspect of this compositionally homogeneous growth of silicon germanium. Okay, and this is the 30% silicon and 70% that's germanium rich silicon germanium. And when you grow this kind of germanium rich silicon germanium, you can grow it even at relatively low temperature. So that the heat interface temperature is fixed as 1028 degrees Celsius, and almost the same temperature gradient implemented, and the growth period is about 300. And these are all the samples before the experiment and after the experiment. So this is a kind of the sandwich sample. This is silicon, and this is germanium and silicon, like that. When you have this kind of sandwich sample, then when you heat it at under this very mild temperature gradient, although the mild temperature gradient is there is a reasonable temperature difference between the feed rate and feed rate, right? So that at this particular temperature, the silicon will not melt, but germanium will melt, because the melting point of germanium is low, right? Then this germanium, in the molten germanium, silicon will dissolve. Okay, and once the silicon dissolves, then the here also the dissolution occurs, and here also the dissolution occurs. But once the dissolution occurs, then the dissolved silicon is lighter than the germanium. That means the density of silicon is almost half of that of germanium. So the dissolved silicon at the feed interface is moved towards the field interface. So that due to the convection process that used to occur at a high temperature of 10,020 degrees Celsius, right? And due to the accumulation of this silicon, dissolved silicon at the feed interface, the dissolution at the feed interface is decreased. Okay, so such kind of the phenomena used to occur during this kind of silicon solution formation. And once the solution is formed, then the silicon will be more at this feed region, feed region. Then the concentration gradient will be there. And due to this concentration gradient, the dissolved silicon will transport towards the feed interface by diffusion. And the concentration will be increased at this feed interface, then the feed interface, and the solution gets supersaturated. Then the growth starts from the feed interface. So that's the growth process which is and this is the the cross-section view of the grown sample. And look at that the cracks are more in this grown sample compared to this one, right? So here the cracks are not up to the level, but here the number of cracks are there. That's mainly due to this germanium rich silicon germanium, because the germanium is larger than silicon. So that but the germanium rich silicon germanium is growing at the silicon feed interface. So the silicon is having a different lattice constant, and silicon germanium with the germanium rich phases having different lattice constant. And due to that, the lattice mismatch will be there. And this lattice mismatch will create a lot of lattice strain, and that relax through this crack formation. Okay, so like that, the cracks are observed in this germanium rich silicon germanium. And again, the composition is measured both in radial and growth direction. And again, the composition is quite homogeneous in both radial as well as the growth direction. So that shows the compositional homogeneity of the sample, and this mild temperature gradient approach is quite beneficial for having such kind of compositionally homogeneous silicon germanium. And this is the the germanium composition fluctuation, and this is applied temperature gradient. So we have conducted this kind of experiments at the different temperature gradient, and when you have this kind of low temperature gradient, that is very mild temperature gradient, then the composition fluctuation can be decreased. Okay, so from this we observe that this is the kind of optimum value, and maybe you can ask what will happen when you decrease the temperature gradient below this 0.4 degrees. That's also we did, and we got some contradict results. Maybe let me show you in the coming slides. But this is the optimum level. So after that, you can able to have the low composition fluctuation, and you can implement this temperature gradient and to grow compositionally homogeneous. As I have shown in the previous slide, what will happen when you decrease the temperature gradient below this point? So that is, this is 0.4 degrees Celsius per mm, right? Then we just implemented almost half of that gradient. That means 0.2 degrees Celsius per mm. And then we just conducted the experiment for this silicon rich silicon germanium, silicon 0.7 and germanium 0.7. And to have this composition, we just increase the growth temperature of about 1200 degrees, right? And then look at that, the gradient is only 0.2 degrees Celsius. So the temperature difference between the feed interface and feed interface is not so high, only extreme, very low. So that the temperature at the feed interface and feed interfaces are very almost close to each other. Okay. So in that condition, we just conducted the experiment, and this is a sample before the experiment, and this is a sample after the experiment, and this is a process review of this sample. Okay. And look at that. This is completely opposite, and the seed crystal was completely dissolved. There is no remaining seed crystal here, whereas the feed crystals are almost remain the same. So that means the reciprocal process was occurred, and the opposite process was occurred. Actually, our intention is to grow the silicon crystal from the seed interface, and that's what occurred in the up to this experiment, the previous experiment, even for this experiment also, because there is a reasonable temperature gradient, and the temperature of seed interface is relatively low compared to the feed interface. So after the initial dissolution, the supersaturation occurs at the seed interface, and crystal starts to grow at the seed interface. But what happened at this very extremely low temperature gradient, the seed was completely dissolved. And because of the complete dissolution of seed, the supersaturation occurred at the feed interface, and the growth occurred from the feed interface towards the seed interface, almost opposite direction compared to the previous experiment. So this is a very unexpected result, and then we just we understood what happened. To understand the growth process, we just taken this EDX mapping of this map. And look at that, this is the grown region, and in the grown region, almost this is the homogeneous region, right? So this homogeneous region is at the feed interface, and almost the seed is completely dissolved. So there is a composition fluctuation and island growths are there throughout the seed. So what happens during this kind of very mild temperature gradient? We just shown this kind of animation. And look at that. This is the silicon seed, and this is silicon seed. Silicon seed at the bottom, silicon seed at the top, and in between there is a germanium. Then what happens? The melting point of germanium is about 936, and this is about 1400, right? And please remember, the density of silicon is almost half of that, even less than half of that germanium, right? So in this condition, what happens? Because initially the germanium will melt, and in the molten germanium, the silicon will dissolve. silicon will dissolve into this germanium, the silicon germanium solution. But in this kind of very mild temperature gradient, what happens? Almost all this silicon or the dissolution of silicon is more, and the dissolved silicon are accumulated at the feed interface because the density of silicon is lower than that of germanium. So almost dissolved silicons are accumulated at the feed interface. So the germanium silicon concentrations are higher at the feed interface, and germanium concentration are more here at the feed interface. So the dissolution at the feed are continuously occur, whereas due to the accumulation of dissolved silicon, the availability of germanium for feed dissolution getting decreased. And because of that, the feed dissolution was suppressed for the period of time, whereas the feed dissolution was increased for the period of time. And due to that, the complete feed dissolution was happening. And once the feed dissolution occurred at certain growth temperature of 1200 degrees Celsius, then this solution gets supersaturated. And since the accumulation of germaniums are more here, then then the constant and the temperature gradient is also very low, so that the supersaturation reached here, and there is no the temperature gradient to drive the concentration from the hot end to the cold end. So that and the temperature is almost same between the feed and feed interface. So the growth occurs at the feed interface towards the feed, and that's what here. So this is the the mapping of the ground region, and this is the composition along the radial direction we measured, and this is the direction where we measured the composition along the growth direction. And look at this. This is the growth direction. The composition is quite homogeneous from the feed interface towards the feed interface, up to about 5 to 7 minutes. Right. After that, the composition is fluctuating. Right. So the composition is quite homogeneous almost in the radial direction. So the homogeneity we have obtained, but the feed was completely dissolved. So the 0.2 degrees Celsius per minute gradient is not appropriate one for growing the crystal from the feed interface towards the feed interface, although the composition homogeneity has been. Okay. And why we obtain this kind of island growth at this completely melted? And look at that, to understand that, we just measured the composition profile of one island, and that is here. And look at that, at the interior part of the wafer, the germanium composition is more. Okay, and the silicon composition is less. So that means the germanium composition, germanium is having low melting point, and silicon is having high melting point. And during the post-growth cooling, so initially the germanium, the silicon will freeze, and by trapping the germanium liquid in between the frozen silicon. And then at low temperature, the germanium was crystallized. So that this kind of germanium-rich island growth was there during this kind of process. And this is silicon germanium phase diagram, and this is how this kind of the island growth will occur. So this is the 1200 degrees growth temperature, and when you decrease the temperature, initially silicon will crystallize, and later germanium will crystallize. So that kind of the variation in the solid temperature of silicon and germanium, we observe this kind of island growth in the post-growth cooling process. And we have measured their structural features like how the lattice constant, the structure of this alloy, and from this study pattern we observe the composition from the lattice constant to be 0.27, which is quite comparable with the initial composition of the sample. And we have used the same compositionally homogeneous silicon germanium to prepare the magnesium silicon germanium. This is one of the low temperature thermoelectric materials. And if you have the compositionally homogeneous silicon germanium, then of course we can prepare compositionally homogeneous magnesium silicon germanium. So for that we have used this growth chamber at a high vacuum, and this growth chamber we have used the compositionally homogeneous pre-synthesized silicon germanium with a magnesium pellet, and we just heated at high vacuum at about 500 degrees Celsius. So at that high vacuum, the magnesium and silicon germanium reacted, and magnesium silicon germanium was formed. And this is the magnesium silicon germanium sample, and the composition has been measured at a different position. And look at that, the composition is also quite homogeneous except a few positions for this magnetic silicon germanium, where we have used the silicon germanium of 50-50 sample, and the silicon 70-30, silicon germanium 70-30 sample have been used to prepare the magnetic silicon germanium at the composition, silicon rich composition, and that is also quite homogeneous. The required sample shows the homogeneity in the composition throughout the sample. Okay, so like that, we have used this magnesium silicon germanium and the silicon germanium, and this is structural features of this magnesium silicon germanium, and we have made it as a pellet by using this STS process and by high pressure and short duration and high temperature, and we got the pellet. And we have used the pelletized samples to measure their electrical resistivity, and this is for pure silicon, and this is for pure germanium, and it shows germanium shows low resistivity compared to silicon due to the variation in the band gap of silicon and germanium, right? And the resistivity of silicon germanium is in between the silicon and germanium, and that is not very not much varied about the temperature. That shows the alloying nature of this sample. And SPECTROPHYSICS coefficient of this sample has been measured by placing the pelletized sample in between the heating and non-heating. Okay, and when you place this kind of heating and non-heating end, it measure the temperature difference by using the thermocouples at hot end and cold end, and by using the probe, you can measure the voltage difference, and then by using that, you can able to compute the thermopower, right? And that's plotted here. And look at the very the valid information is here. For magnesium silicon germanium, the SPECTROPHYSICS coefficient is quite high at the low temperature region, whereas for silicon germanium, the SPECTROPHYSICS coefficient is quite high at the high temperature region. So that kind of the variations are there. So which confirms that the magnesium silicon germanium can be used for low temperature application, and silicon germanium can be used for high temperature application. So when you have this kind of combination of silicon germanium and magnesium silicon germanium, we can have the cascaded system of this magnesium silicon germanium and silicon germanium to harvest more thermoelectric performance. Okay, and like this, we have prepared the samples and we have studied, and there are this is the future of thermoelectric technology. That means the thermoelectric efficiency can be enhanced as a function of year, and there is a scope of increasing the efficiency even beyond 50% of efficiency. And there are different kind of thermoelectric materials are coming out, and if the thermoelectric ZT is increasing, then the overall efficiency can be increased. So like cobalt antimonide, and recently thin telluride and thin selenide, like the germanium telluride, like that, there are coming different kind of thermoelectric materials are coming out with high ZT, and that will lead to improve the overall performance, and then we can able to increase the applications of the thermoelectric technology for variety of applications. Okay, so I'll stop here. So if you have any questions in this silicon germanium and germanium, please. Or if you want, I can continue further.
Yes, sir. You can continue, sir.
Okay.
So, dear participants, do you have any questions?
Okay. Shall I? Shall I continue?
Yes, sir.
Okay. So this is the silicon germanium phase diagram as I have shown in the previous slide. And this is the importance of this mild temperature gradient. Actually, when you grow this kind of crystals under this cheap temperature gradient, if there is a temperature gradient of about 100 degrees Celsius between this CDN and PDN, then the dissolution occurs in the molten germanium and silicon germanium solution will form. Then this dissolved silicon from the feed interface will diffuse towards the feed interface. Then the supersaturation will occur and growth will start, right? And when the growth proceeds, the growth temperature will increase towards the high temperature. And due to that, the composition of the resultant crystal will vary along this line, the solidus line of this solidus curve of this silicon germanium phase diagram. So when you have this 100-degree temperature difference between the feed and PDL, then the composition of this alloy will change from 0.54 to 0.34. So this is really a very drastic change of composition. So when you have this kind of drastic change of composition, then all the respective properties. Okay, so this when you have this steep temperature gradient, so this kind of the huge difference will be there. To avoid that huge temperature difference, composition difference, there are different strategies that people have followed so far. Like instead of to avoid the temperature fluctuation, they try to move the growth interface by matching with the growth rate towards the by lowering the amplitude. Like that, they keep the ultimate aim of having the higher composition homogeneity is that to keep the temperature at the interface. So as a constant. So if you want to keep the interface, there are two ways: either by moving the amplitude along with the growth rate, then you can keep the temperature, or by moving the furnace, you can keep the temperature. But both during this kind of movement process, the interface is possible to get destroyed. Okay. So in that case, we can avoid the temperature fluctuation of the growth interface by implementing this kind of very mild temperature. So when you reduce this temperature difference between the hot end and cold end, then you can able to avoid the temperature fluctuation at the hot end, at the growth interface. And that can be done by using this kind of mild temperature gradient. And that's what we implemented in the silicon germanium. And we obtained that kind of very compositionally homogeneous silicon germanium. These are already seen. Just I want to show here about this gallium doped silicon germanium, because the silicon germanium is intrinsic semiconductor alloy. But if you want to make it as a p-type and n-type, to make it as a device, then you have to have kind of polarity in the sample. That means you can dope gallium as a dopant to make it as a p-type silicon germanium. And for that, we did the experiment by properly tuning doping the gallium with 120 of 18 atoms for Q2. And we have grown the sample like this. And this is the cross-section view of the sample. And this is the grown region of silicon germanium. And we measured the composition. Again, the composition is quite homogeneous along the growth direction, except at the seed and feed interface. Why this fluctuation is there? That's mainly due to the crack propagation. So the cracks are here at the feed interface as well as at the feed interface. So these cracks are mainly due to the lattice mismatch between the silicon and the silicon germanium. Okay, and this is also the composition is quite homogeneous along the radial direction except the crack region. So that shows the composition homogeneity of this sample. And this is the gallium doped silicon germanium, which shows the composition homogeneity in the mapping. And another one is that this kind of the etching analysis. So we did the etching of the sample at a different position, and this is the etched surface near the interface, about 2 mm above the interface, and this is at the center, and this is at the 2 mm below the interface. And look at the HP density. These are the HPs are there, and the HP densities are more near the interface compared to the center region. And in addition to that, there are a lot of cracks and grind boundaries are there in the samples. And these kind of cracks also less at the center part of the sample compared to the interface. So near the interface, there are a lot of cracks as well as HPs. So this is the position at a different the region at different position, like near the interface, center, and near the feed interface. So the EPD densities are more at the interface compared to the center. So we have taken this sample at B position, sample B and sample C for thermoelectric analysis. The sample B is near the interface, it is having a relatively high EPD, and this is at the center, it is having low EPD. And then we measured the carrier concentration and mobility and resistivity. And the carrier concentrations are almost same for all these sample because the sample are taken almost in the narrow region of the sample. So the carrier concentration are not changed drastically. And the mobility is also not changed along the both directions. But look at the resistivity. The resistivity of the sample B is relatively high, whereas the sample C, the resistivity is relatively low. So that means sample B is the high EPD region and sample C is the low EPD region. So although the carrier concentrations are same, the resistivity is drastically decreased, reasonably decreased compared to the sample sample B. So that means the HP densities are playing a role in this kind of carrier transport. So the HP densities are revealed as a representative of defects. So these defects are, trapping the transport properties, trapping the transporting carriers, so that the resistivities are decreasing, increasing for the high EPD samples. And but the SPECTROPHYSICS coefficient is almost same for all the samples. And the thermal conductivity of the sample has been measured as a function of temperature. And by using the SPECTROPHYSICS coefficient and resistivity and thermal conductivity, the figure of merit has been calculated. So the figure of merit is quite high for the low EPD region compared to the high EPD region sample. So that means, when you have the sample with the low HP density, then the carrier transport will be quite smoother. Whereas when you have the high HP density, then the carrier transport can be trapped or scattered by the defects, so that the net transport will be decreased, and that results low form factor as well as the density of the material. So these cracks and HPs are mainly due to the lattice mismatch between the silicon and the grown silicon germanium. Okay, so like that. So like that, also we used antimony doped silicon germanium to make iron type silicon germanium samples, and we did the systematic analysis to study the carrier transport and the composition homogeneity, and we obtained the reasonable variation in the HP density as a function of the precision. And we measured the thermoelectric characteristics, and the form factor is also quite high, and the thermal conductivity is also quite low. And the figure of merit, we have measured the figure of merit for antimony dope and the gallium dope samples. And this is the figure of merit of the silicon germanium.
Sir, excuse me, sir, your slides are not moving.
Yeah.
It looks ideal.
Now, how about now?
No, sir, it's not.
Yeah, almost come to the end of this lecture. So how about now? Which slide is there?
It's phase diagram.
Phase diagram. How about now?
Yeah, it's fine.
Yeah. So like that, we have prepared the gallium doped silicon germanium and the indium doped, antimony doped silicon germanium, and we studied their defect density and electron transport properties, and we measured their thermoelectric characteristics, and the density of the sample has been improved by controlling the defect density in the sample. Okay. So yeah, I'll stop here. So if you have any doubt, you can ask. Hello.
Sir, thank you, sir, for sharing your experience in the field of Thank you very much, sir, for sharing your experience in the field of oxide nanomaterials. So next we move to session 2. On behalf of PG and Research Department of Physics, Jamal College, We welcome our resource person, Dr. R. Jayavel from Anna University, Chennai.
Thank you, sir. Yeah, I am ready.
Okay, sir. I take this opportunity to introduce our resource person for this session. Our resource person, Dr. R. Jayavel, Director, Center for Nanoscience and Technology, Anna University, Chennai. He is having 31 years of research experience in material science and engineering and 26 years of teaching experience. He has over 15 years of administrative experience as Director, Center for Nanoscience and Technology, and Director in charge, Center for International Affairs at Anna University. He has published about 470 research papers in reputed international journals with the H index of 53, I-10 index of 267, and over 10,500 citations. He has been designated as highly cited author by Royal Society of Chemistry, UK. He visited several countries like USA, UK, Germany, France, Italy, South Korea, China, Taiwan, and Saudi Arabia for collaborative research. He was a visiting professor at the Research Institute of Electronics, Japan in the year 2007, and the University of Göttingen, Germany in the year 2010. He has investigated several research projects worth rupees 12 crore funded by various organizations like DST, UGC, AICT, and DRDO. He has done the consultancy services to industries worth rupees 16 lakh. He has edited book on advanced materials for optoelectronics. He is the chief editor of Journals of Applied Engineering and Sciences, published by Anna University, and managing editor of journal Nano, World Scientific Publishers. He is a recipient of several awards and recognition, like Tamil Nadu Academy of Sciences since 1997, UGC Mid-Career Award in the year 2020, LEAP Fellowship Award, Leadership for Academician Program in year 2019 by Ministry of Education, Government of India, Lifetime Achievements Award in year 2019 by Indian Spectrophysics Association, ISPA, Tamil Nadu Scientist Award in year 2016, Active Researcher Award by Anna University in 2012, Science and Technology Agency Fellowship, Japan in the year 1999 to 2001. He has received Best Presentation Awards at several conferences. He has been the member of several academic and professional bodies. He is also a member of UNESCO Chair in Materials and Technologies for Energy Conversion, Saving and Storage. So with this brief introduction, I request our resource person to deliver a lecture on two-dimensional nano composite functional materials for energy storage applications. I hand over this session to person.
Thank you, sir. Is it my voice is clear?
Yes, sir. It is clear, sir.
Yeah. Okay. So I am very much delighted and honored to have been invited for this conference. I'm in FDP. Okay, I'll just let me share my view. Which is organized by the ISPA under the aegis of Professor S. Gunasekharan. Can I just share the screen because it's not coming?
Yes.
Are you able to see my
No, sir.
slides?
Yes, sir. It is visible, sir. Yes, sir.
Huh? Yeah.
Yes, sir. It is visible, sir.
Okay. Okay. Fine. So, organized by the Jamal Mohamed College in collaboration with Indian Spectrophysics Association. We had a nice inaugural talk by Professor yes, Gunasekaran yesterday, and also a couple of lectures by Dr. Sendil Selvan, Professor Arivanandan. So I am also going to talk about this particular topic, which is very much related to the condensed matter physics. But Professor SG has given a very wide, elaborate um, details about the different aspects of condensed matter physics. And this part is mainly on dealing with the nanostructures for a very specific applications, which is called energy storage applications. Okay, so in fact, I'll be briefing you about our some of the activities which we have been doing at Anna University, and also some of the importance and applications of these very special materials called 2D materials. And if you have any doubt or clarifications, you also feel free to stop me. And I don't know whether we have time at the end, because by what time I should complete, sir? 1:30 or should I?
130, sir. 130, sir.
Okay. Okay, so this is actually some of the energy storage systems which we have been experiencing, and we are all very familiar with this kind of batteries, which is useful for storage applications. And when it goes for long requirement, and we'll have assembly of this kind of batteries assembled in such a way that we can store more energy. But this is something kind of building blocks in a large scale, and for which we need different kinds of technological optimization, or what is called process optimization. But we have a large area battery storage technology is now available. It's on industrial scale. And we also have the grid storage, which I'm sure many of the physicists we know that when you have the very efficient grid, and it is very useful for store the energy in a very efficient way, and also we can significantly reduce the what is called the distribution and transmission path from one place to another place. And when we talk about the environmental issues, that we are also now dealing with what is called green energy technologies, which is associated with this kind of renewable energies like wind or solar, which can be integrated with this so that we can get a energy storage system which is very environmental friendly. Okay. And for realizing all these technologies, the most important thing is about the materials, because unless we have the materials which are all useful for these applications, we cannot expect the technology to be useful for society. Okay, so therefore the materials become backbone for these kind of advanced technologies. And so in this talk, I would discuss about some of the very famous 2D layered materials and applications. Then I'll also discuss something about the energy storage systems which are all currently being used, and what are the futuristic requirements for this material. I mean the technology. And then I would focus on this one particular material called graphene, which is a very famous 2D material, and then how this material behaves when it is combined with metal oxides to make the nanocomposites in terms of its performance and application aspects. And we have recently made some attempt to make this material useful for large scale applications, which we call it as the graphene bucky paper. And then we also demonstrated some functional devices, and I would just discuss some of the devices which we have fabricated in our laboratory, and then finally summarize. Okay, so we know the classification of materials based on different properties, especially if you take the periodic table. We have different kinds of classification, classification based on the group in terms of column, or in terms of vertical arrangement. Then based on the properties, we have different kinds of metals. For example, if we have the classification of metals, we have transition metals, alkaline metals, rare earth metals, noble metals. So we have different kinds of classification based on the material properties or physicochemical properties. And this is actually a classification based on the external morphology of the material. And we are very familiar with what is called three-dimensional morphology. And this three-dimensional morphology is applicable to almost all materials. If we have arranged this synthesis materials by proper methodology or proper optimization process. And if you take a three-dimensional material and if you reduce one of the dimension along this direction, then you will end up what is called a two-dimensional layered materials. And these two-dimensional materials, which are all typically films or plates or sheets with very different properties. And these materials are called 2D materials, which can be stacked to form a bulk material, or this material can also be taken into multi-layered materials. As long as we maintain a few layers or even single layer, then this material possesses what is called two-dimensional nature. And if you reduce another dimension along this direction, you will get what is called a one-dimensional structure. And the typical examples for these one-dimensional structures are tubes, wires, or filaments, fibers. We have plenty of examples under this category also. And we have a variety of materials which can be prepared in one-dimensional structure. And these one-dimensional materials will have a very high aspect ratio. That means the ratio between the length and breadth or thickness is very extreme. And many of you are very familiar what is called the zero-dimensional materials also. If you reduce another dimension along this direction, then we'll end up with a small physical entity called zero-dimensional material, which is also called as quantum dot materials. And this is very specific with respect to nanostructures. And these kind of materials are where we can just have the thickness in the nano region, and then length can be micron size. Similarly, the thickness of the sheets can be in the nano region, and the length can be, breadth and width can be of large scale dimensions. So this kind of materials are very well known for a variety of applications, and we have today these materials which are all available in pure form, or we can also have the coated forms, or we can also have the one-dimensional structures with the extended morphology to meet the two-dimensional materials requirement. Okay. So these are the classifications, and today I am going to discuss only about this particular material and how this behaves and their properties, etc. 2D materials are, as I said, it's a special class of materials. We have a variety of materials under this category. We have different kinds of graphene is the base material, which is known for almost for the past 15 to 16 years. Then we have the tungsten sulfide, disulfide, and tungsten diselenide, molybdenum disulfide, hexagonal boron nitride, and transition metals, chalcogenides. These are all actually very recent materials which possess this 2D category, and these materials are listed here also. And apart from that, if you just look into the outer circle, we have different kinds of silicates, silicene, germany, and metal oxides for ternary or quaternary metal oxides. Then we have enzene. Actually, this is a family of materials which has got a lot of expansion. Then black phosphor and DLC, diamond-like carbon. These are all actually known materials which are all very familiar with respect to very specific applications, and these materials also now being evolved in a very big way. Okay, and if you take these materials, why it is all interested means that normally these materials will have 2D layered structures, and these layered structures can be separated into individual layers. by proper optimization process. And this layer can be considered as a single layer. Then it becomes what is called a layered structure. And we know that the bulk material, which has the dimensions of the order of millimeter or micrometer or even a few hundred nanometers. So these layers, which are all basically less than 1 nanometer, because we know the atomic dimension, which is of the order of few angstrom units, and an individual layers thickness is of the order of few angstrom units, which are already in sub-nanometer scale. And this sub-nanometer scale particles or structures can be arranged to form a bulk. And when we have this kind of arrangements, the bulk structure, which is made up of these individual layers, will have a lot of interesting properties. At the same time, it will also need a lot of optimization in terms of its structure, or in terms of its defects, or if you have the individual layers, then the interface properties or interface layers are these are all basically porous structures. The porous or hole engineering. And if we have stacking of these layers, how these 2D structures are stacked together, there are different kinds of problems associated with this kind of materials. So nevertheless, if you look into the application aspects, as I said, for example, if you take hexagonal boron nitride, this will have highly insulating property. And the materials like MOS2, tungsten diselenide, which will have a typical semiconducting property with the energy gap of about 1 to 2 electron volt. And some of the materials behaves like half metals, and some of them are semi-metals like graphene with zero band gap energy, and some materials like which is very perfect metallic structures, and some of them will have a very extreme conductivity, and these materials will have what is called superconducting properties. Okay, so this will have a very diversified properties, and hence applications also very wide. And if you take the just the absorption property of this material, it almost covers the entire electromagnetic spectrum, ranging from UV to visible, visible to NIR, mid-IR, far-IR, terahertz, and microwave frequencies. Okay, and therefore these materials will have a lot of interesting applications, and that's what people are interested in working in these materials. Some of the applications, very prominent applications of these 2D materials are, as I said, these materials are multifunctional materials, where we can use it for communication applications, or digital or analog circuits, and it can also be useful for interconnects in electronic devices, and it's also useful for memory applications, and we can use it for sensors also. Okay, and this kind of multifunctionality is the uniqueness of this material, and because of the two-dimensional nature, this is actually highly flexible, and therefore we can have different kinds of flexible application possible, right? Transparent conductors, flexible touch sensors, and light emitting devices, then wearable touch sensors and concrete reinforcement. We have a variety of application possibilities for this material. Okay. When it's coming to the sensors, we have different kinds of sensors like electrochemical sensors, fluorescent sensors, field effect transistor sensors. Not only these are all actually very prominent sensor applications. Other than that, we have electrochemical luminescence sensors, photoelectrochemical sensors, colorimetric, pH sensors. We have different kinds of sensors used in a device based on this 2D material. And coming to the electronics area, we have very interesting application possibilities, because as a physicist, we are all very familiar with what is called VLSI technology, very large scale integration devices. And this VLSI technology are now moving towards what is called ultra large scale integration devices. And this ultra large scale integration devices are now taken to the ultimate limit of what is called extremely large scale integration devices by use of this kind of 2D materials. So the reason is that when we have the extremely large scale integration devices, so it means that we can integrate millions and millions of transistors in a single chip. But when we just follow the conventional technology, it is we cannot have 1 million transistors or 2 million transistors fabricated and then integrated in a single chip in isolation. That was not possible. But what they do is they just make this kind of material where that each and every electron in this material can act as a transistor, and therefore it is possible to integrate millions and millions of electrons together. So therefore we have the extremely large scale integration devices possible. Okay, and coming to biomedical, we have both therapeutic, imaging, actually sensing applications. To some extent, these materials can also be useful for biosafety applications. And in photonics, again, the two-dimensional materials will have a lot of interesting applications because of its flexibility and also the compatibility with different materials. So that there are a lot of photonic devices fabricated using these 2D materials. Okay. As I said, we have different kinds of 2D materials, and among them, one of these materials called graphene, which is very well known during the last 2 decades. And this was first synthesis in laboratory by these two Russian scientists who are working in the University of Manchester. And they got the Nobel Prize in Physics in 2010. Okay, so literally this material is known for the past 16 years or so. And this is the typical graphitic layered structure. And this graphitic layer has a layered structure like this. And if you optimize the process in such a way that if you're able to isolate this particular basal plane, and this becomes atomic thick plane of graphene, and the morphology looks like this. And the raw material used to prepare this 2D structure is the natural graphite. The natural graphite is available in abundance, and we have to only use this kind of natural graphite to prepare this graphene. Okay. And basically, the graphene is a two-dimensional hexagonal lattice of carbon, and which is arranged in the sp2 hybridized carbon atoms. And we all know that carbon bonding is the strongest known bond in nature, and therefore these materials will have a very high mechanical strength or mechanical properties, and hence it has got a lot of application potential from graphene electronics, lithium-ion battery. Then it has got a very high photocatalytic properties, and then we can use it for energy storage applications in supercapacitors. And people also demonstrate the OLEDs, organic light emitting diodes, using this kind of materials. And recently, this graphene oxide has been proven to be a very strong antiviral coating, and which is especially coated on face mask and personal protection equipment like PPEs, especially for the protection from COVID-19. And other than that, we have a lot of medical and biomedical applications also. Even though this particular material, which is known for the laboratory scale usage since 2004, there is a recent news that this graphene is probably around 4.5 billion years old structure, which is coated naturally on these meteorites. And therefore, the NASA's Johnson Space Center has, in association with the Carnegie Institution of Washington, they discovered the graphite embedded between these two kind of structures, which contains centuries old minerals that was the creation of this Earth or planet like that. and which was also verified by another independent group based in Japan, which is called the Institute of Tokyo Institute of Technology. And also one of the members of the team was also an Indian origin student. And they also parallelly studied and discussed the age of this kind of structures. Okay, so even though these materials are known for many centuries or many very long history, and their usage has become very evident in the recent days. And we have been in our laboratory, we have been working on this material on 4 verticals. One is about the graphene FET sensors, and we use to fabricate the electronic devices based on sensors. And the useful application is, it is not a conventional chemical sensor or humidity sensor or gas sensors. It was all useful for very extreme environments like DNA hybridization sensing, high energy radiation sensing kind of materials. And another interesting application is about the photocatalysis, because as I said, these materials will have very high surface area of the order of 2000 to 3000 meters square per gram, and hence it will have a very strong photocatalytic activity. And we have been using this material for a variety of photocatalytic properties, and also it is useful for energy storage through water splitting and hydrogen production. We have a variety of activities going on. And this is about the graphene quantum dot integrated structures, which is a very special structure, which is now being considered very potentially as a replacement for conventional silicon technology, because the silicon technology is the mature technology where we can achieve almost 20 plus percentage of conversion efficiency in the module stage. But the only difficulty was when we follow the silicon technology, when we wanted to harvest 1 kilowatt of energy, we need at least 1 square meter area. And so therefore we need a very huge space for installation, large installations. And recently you can just see wherever we have space, like the airport or riverbeds and rooftops, wherever we have space, we are trying to install these silicon panels so that we can enhance the renewable energy capacity. But this structure has been theoretically studied, that this is actually a graphene layer which is integrated with a quantum dot layer. And when we have the cascade layers like this, and if you just calculate the amount of photoelectrons observed on the surface of this layer of area of about 10 square centimeter, which is almost equal to 1 meter square area of silicon panels. That is the theoretical prediction which they have made recently. And it's also possible that we can make a heterojunction solar cells using this kind of materials, but the conversion efficiency is very low. It is in the at least probably less than 10 percentage. But it needs a lot of optimization process so that it can meet with the the commercial standard of about 20 plus percentage of conversion efficiency. And this is actually the energy storage aspects which we have been working in our laboratory. And we have moved from graphene to MOS2 and tungsten selenide kind of thing. And this in this talk, I'll be mostly talking about these supercapacitor aspects. Okay, so let me just start with the energy storage systems. And I'm sure that you are all very familiar with this slide, where we have now the battery operated vehicles everywhere. We have a lot of startup companies, they produce this, manufacture these electric vehicles. And the expansion is going on, and we have developments happening in every day. The major requirement is about the battery, okay, because the battery power depends, determines the speed of the vehicle, and also it is related to the cost of the vehicle, okay. And as such, we have two-wheelers, then three-wheeler, four-wheelers, and even passenger vehicles are also made up of this electric batteries. And in all these vehicles, we have the lithium-ion battery, which is predominantly used for vehicles. And obviously, if the power is higher and the storage capacity is higher, then we have price also going up accordingly. Okay, and these are all already available in that. But this lithium-ion battery was discovered in 1970s, and it was commercialized in 1991 by Sony Corporation. And the discovery also got the Nobel Prize in chemistry in 2019 because of the wide range of industrial scale applications. And today we have lithium-ion battery manufacturing spread over the entire globe, with the maximum productivity from Asia Pacific. Asia Pacific means in China, basically. Okay, so Europe, they have North America, they have a lot of companies, and also it started growing up from South America, Middle East, and African countries. And the major contribution is from China. And overall, the global market rate in 2019 was about 7 billion units per year. Okay, and but the trend is because everywhere that electric vehicle concept is growing up, and so therefore, obviously, this battery technology has to be developed in the large scale to meet with the latest requirements. But as far as our country is concerned, the biggest challenge for the mass adoption of electric vehicle is the price, because the cost of imported battery is very exorbitant, and unfortunately we don't have lithium rich in our country, but only a few places like Godavari belt and Mandya in Karnataka, in Rajasthan. So they have just discovered a kind of isolated lithium ores, but to meet with the requirement of the current trend, because the government of India has brought out the electric vehicle policy, and state government also we have the policy, and the policy says that by 2025 almost 60 to 70% of the passenger vehicles should be on electric vehicle base, and by 2030 100% private like own use vehicles should be of electric vehicle, leaving the commercial or public transportation. So in order to meet with the requirement and the current level of import of lithium batteries is very, very alarming. And therefore, if you just look into the, this is the import cost from 2016-17 to 17-18, and 18-19 was the peak. And the government has discussed in a serious way, and then they decided to bring down the import cost by in 1920, 2021 by encouraging the indigenous development of these batteries. Okay, so since 2018, there are a lot of efforts to develop the indigenous battery technology. And in fact, this was actually an MOU signed between the Central Electrochemical Research Institute, Karikudi, and the Rasi Solar Group based Bangalore. They have a tie-up to establish the battery manufacturing facility near Tamil Nadu, Karnataka border in Krishnagiri district. And it was actually, the MOU was signed in 2018 itself, and because of various reasons, and also because of this pandemic, and the facility is yet to roll out the products, but the development is going on now. And apart from that, we have ISRO, which is venturing into a large scale lithium-ion battery technology, especially to supply the automobile sector. And Indian Oil Corporation is developing batteries from the indigenous metal to powder to power the India's electric vehicle ambitions, because the government has made a policy and it has to be supported from different corners so that the prediction can become reality. And we have different startup companies also, hundreds of electric vehicle companies which are all coming up and focusing on components or storage stations and hybrid level of kind of battery technology like that. Okay, so it is actually the combined effort of private and private partners, government, and actually public sector enterprises. And it is a collective effort that we have to develop the indigenous lithium-ion battery technology to meet with the growing requirement of electric vehicle development. Alternatively, as I told that we have very limited sources of lithium, and even if the technology is developed, then lithium has to be imported. So therefore, the alternate battery materials are also being evolved, and we have different kinds of materials like transition metal oxide, different kinds of phosphates and polyamides, and sodium-based materials, transition metal oxides, metals alkogenates, hard carbon, and a variety of different kinds of alloys. And most of these are basically 2D materials. Okay, whether it's the Nasicon type material or layered transition metals or transition metals alkogenates. These are all basically layered materials, and we have iron-based batteries also being evolved. And this kind of material also is very because iron can be prepared easily, and iron ore we have in abundance. Therefore, there is also technology coming up, and air batteries also being evolved. And then we have sodium, sulfur. Variety of materials available for this alternative technology to lithium-ion battery, but it takes time for every technology to come up in the commercial scale. As I said, lithium-ion, known for discovered almost in 1970s and commercialized after 20 years, now being used in a large scale usage. Okay, so like that, this is also coming up. So therefore, we hope that in future we will have we don't have to depend only on lithium-ion battery. And another reason is the lithium is highly volatile material, and also it is explosive. And those who had performed the air travel probably would have heard that you are not supposed to carry the lithium-ion based electric gadgets in your baggage. Okay, and you are permitted only to take it in a hand luggage because of any explosive possibilities when it is subjected to very extreme conditions like pressure and temperature. Okay, so alternatively, the storage technology is also being evolved. Other than batteries, because the supercapacitors which is called supercaps, which was also known for the past 20 years or so. These supercapacitors advantages, the name itself implies that the capacitors in the very extreme level. Okay, and if you just compare the conventional batteries, whether it's a lithium-ion battery or sodium batteries or any kind of batteries, we can achieve a very high energy density, but the power density is very much limited. And this is the case for the fuel cell also. And if you have the conventional capacitors, the capacitors which we use in our laboratory, which is written as a microfarad. Okay, then that means the capacitances of the order of 10⁻⁶ farad. Whereas this kind of supercapacitors or ultra capacitors can have the capacitance of almost 9 orders of magnitude higher than the conventional capacitors, so that it can reach almost to 10 power 2 to 10 power 3 order of capacitance. So more than that, we can also enhance the energy density to reach on par with the level of batteries and fuel cells, and that was the advantage of going for these supercapacitors for energy storage applications. And another thing is like when we have the conventional battery, the charging and discharging takes place a very long time. And that was the reason that the electric vehicles mobility is now restricted within 100 to 150 kilometers because we don't have a large level storage mechanism to drive these vehicles on a longer duration and also larger distances. But the supercapacitors can have a very instant charging, and also discharging is also very possible, so that even heavy vehicles can be taken at a very faster speed by the instant discharge of the energy from the storage medium. And coming to the materials aspects, the supercapacitors are classified under two categories. One is the double layer capacitors, where the charge storage takes place by electrostatic process, or the material is called as Helmholtz layered materials. And if we have the energy storage by electrochemical process, then that is called pseudo capacitors. And of course, electric double layer capacitors will have more stability, and pseudo capacitors will have more capacity in terms of energy storage device. But for the double layer capacitors, we have mostly the carbon based materials like activated carbon, carbon aerosols, carbon nanotubes, graphene, and these kind of materials. And for pseudo capacitance, conducting polymers and metal oxides are prominent materials. But the polymers will have more flexibility, and also metal oxides, it's very difficult to achieve the stability, except a few materials like ruthenium oxide and other things. Other materials are highly flexible. So in order to have more stable electrode with also better performance in terms of storage capacity, we go for the hybrid capacitors. So where the storage takes place both by electrostatic process as well as electrochemical process, and which can be achieved by the combination of these two categories of material, right? Okay, activated carbon combined with polymers, or carbon nanotubes combined with metal oxides, graphene combined with metal oxides, like that. Okay, and we can make hybrid capacitors. And this is the typical schematic, where if you take conventional electric double layer capacitors, you have same material both for anode and cathode or current collector, separated by electrolyte. And if you have pseudo capacitors, this is actually polymer based or metal oxide based things. And if you have a combination of these two, then we have the carbon based materials as well as the polymer based materials to have the hybrid performance. And the hybrid vehicles will have advantages, because, as I said, we can achieve more energy density as well as the power density for especially for high-end applications. So if you look into the evolution of supercapacitor opportunities or developments, as I said, it was started in 1995 that supercapacitors were potentially used for electric vehicles, and it was demonstrated in Russia. And in 2004, the Shanghai Tech Park developed the fast charging system, charging, discharging supercapacitors. And in 2006, it was into commercial usage, especially for hybrid electric vehicles. And then today, this becomes a very important commodity to expand the electric vehicle mobility in large scale. Okay. And in 2019, then rechargeable supercapacitors were also developed by United States, where we can have this kind of capacitors recharge instantly, and also the recharge can also be done when it is in usage. So it's actually double advantages, where we don't have to wait for the recharge to happen after stopping the vehicle, and then inbuilt system can just have the supercapacitor charged instantly while it is in the move. Okay, so this is about the development of supercapacitors. But when you look into the application aspects, it was started as small scale applications like memory backup and instantaneous power requirement. So largely now this can be used for energy storage in large scale, and as I said, this supercapacitor can also be used for grid storage in renewable energy sector, and high-speed vehicles or large-scale vehicle movement also like this. Okay, and this is actually the performance comparison of the energy storage devices compared to capacitors and batteries, and in all aspects the supercapacitors perform well. And we have when you have traditional supercapacitors, the hybrid or asymmetric supercapacitors has much more advantages in terms of energy density, reaching almost 20 to 40 watt hour per liter, and with the maximum operating voltage, and then the self discharge is also very, very low. Okay, and that means it's almost stable. Okay, we don't have to worry about the self discharge of this supercapacitors. Okay, compared to other materials. Right. So the if you look into the market share during this 2014 to 2020, there is a phenomenal increase in the automotive sector. Just to see, this is actually the automotive sector. In 2014, it has just gone to almost covering 40% of the requirement for automotive industries. Then other than that, we have the hybrid transport and other renewable energy sector, infrastructure, grid balancing for the grid storage systems, and of course the most part is about the electronics applications, where it has got different kinds of usage. The futuristic application is for these supercapacitors can be potentially useful for aerospace and defense applications, and which can also be useful for the generation next high-speed trains, where we can will be able to operate the train over 500 to 600 kilometers speed. Okay, this is the future requirement, and but as of now, the electric vehicle mobility is mainly covered with the supercapacitor. The advantage is that we can achieve a very high power density compared to the lithium-ion batteries, and also the stability or the lifespan is almost 10 times that of the battery technology. Coming to the materials for these supercapacitors, as I said, I have just given only the flavor of 2D materials, but other than 2D materials, we have different kinds of materials available for these supercapacitors. Carbon-based materials like activated carbon, carbon aerosols, carbon nanotubes, graphene, and whatever the new developments happening in these carbon-based materials. We have hundreds of conducting polymers available, and we have different and varieties of metal oxides, starting from iron oxide, tin oxide, manganese oxide, nickel oxide, zinc oxide, titanium oxide, manganese oxide, ruthenium oxide. We have plenty of metal oxides. And the ruthenium oxide, among different metal oxides, ruthenium oxide will have a more compatibility with the carbon-based material, especially activated carbon or carbon aerosols or CNT, carbon black. Therefore, the combination of ruthenium oxide with the metal oxides can take the ultimate level of the specific capacitance of almost 10 power 3 orders of farad per gram. Okay, but the challenge is that ruthenium oxide synthesis is also very difficult, and our material is also very exorbitant. Raw materials are exorbitantly costly, but still it is worth to spend money on these lithium-based materials for development of hybrid supercapacitors to achieve maximum specific capacitance of 1200 farad per gram or something. Okay. Other than that, we have metal halides, which are all typically two-dimensional structures, which is useful for not only energy storage, we can also use it for energy conversion, and including photovoltaics, catalysis, batteries, supercapacitors, and hydrogen storage like that. Okay, and of course there are large scale industrial scale developments happening with this metal halide perovskite oxides, which Professor Arivanandan also explained about the thermoelectric properties and functionalities of these materials. I would just concentrate on only the 2D materials as of now, and when we have this the process optimization includes materials development, and of course if we have the new materials which also contribute for the material sector, and then the electrolytes, which is very important for because the stability of electrolyte only determines the stability of the supercapacitor or any storage device, and the application aspect is also now widening. Not only for energy storage, we can have these supercapacitors for safe memory and other healthcare devices or microbial devices kind of thing. And the most important thing is about the charge storage or the capacity with which the systems can be used. Of course, the future challenges is also another area where people are interested in looking into that to take it in the next paradigm. Okay. When we have this material, the process optimization is very important, and also it is very complicated because starting from the cell performance, including the cyclic stability and the time constant, and also the energy density, power density, the maximum peak power density, peak power energy density and power density, optimization of the operating voltage window, then specific capacitance. There are plenty of process involved in this the system to be useful for commercial applications. Therefore, those who are interested in working on these materials, they have plenty of opportunities to work on very specific, because there are people working only on the increasing the density of the electrode, or to reduce the thickness of the electrode so that the compactors or ultra miniaturization can be possible. And packaging is also another area where there are a lot of interesting work, because the packaging industry, they have a lot of interest. The Ministry of Food Processing and Packaging industry has come up with new innovative technologies for the long-term sustainability of the packaging these things. Okay, right. Yeah. Sorry, I have to just sign an important check, and the office people interrupted me. Sorry for that. Okay, so now just let me focus on the graphene, which I told you that I'll be that we have been working on this material. The advantage of this graphene is that we can achieve the large surface area of about 2,600 meters square per gram, and obviously it will have a very high electron mobility because of the zero band gap at room temperature. and very high thermal conductivity, and also because of the flexibility and 2D nature, it has a very high elastic modulus. Okay, and the supercapacitor performance is determined by the mostly the parameters like electrical conductivity, capacitance, then cyclic stability for large scale charge discharge cycles, and the mechanical stability, and also the easy integration for system development. So when you just look into all these parameters, the graphene outperforms with respect to other materials, and so this is actually the the graphene supercapacitor based concept, where we can have different kinds of application possibilities, and also we can have different kinds of avenues to for optimization or the upgradation of the performance. Okay, so let me just brief you something about the synthesis of this graphene, how this graphene can be synthesized. As I said, the raw material is the natural graphite, and once we have the natural graphite, there are plenty of methods available where we can extract the graphene. One is the mechanical exfoliation, which almost leads to a single layer graphene without any stacking. And the thermal exfoliation can also be followed when we just heat the surface, where we can isolate the top layer. But many a time it will be difficult to have the single layer thermal conditions. And the liquid exfoliation is also easiest way that we can do it by taking the liquid and then just sonicate it for about a few hours, and then extract this one by heating. And microwave assisted growth, and the solothermal or hydrothermal method, which is also useful depending upon the solvent which you use for this one. And CVD is a kind of sophisticated technique where we can use it for deposition of these graphene layers on a substrate. And chemical reduction is a very convenient and also very inexpensive way of producing this graphene from the natural graphite. And I'll just give one example how this chemical reduction process is used to do this. And the people also, as I said, the hydrothermal reduction or in situ reduction process is also very efficient in reducing the graphene oxide into graphene. And electrochemical synthesis, and people also use the ion implantation for the preparation of these graphene layer structures. And even though we have a variety of methods available, but the one important thing is, as far as the graphene structure is concerned, you can choose the proper appropriate methodology based on the application. Okay, because it will have each technique can have some advantages of going for single layer or stacked layers, or more stable or more flexible. So therefore, the synthesis process is determined based on the applications. For example, if you want to use it for sensor applications, the most appropriate method is they go for liquid exfoliation. And for flexible applications, mostly the CVD grown graphene films are used. And for transistors or FET or memory devices, the CNT unizipping process or surface patterning or etching the graphene surface also another area. And you want to use it for supercapacitors or solar cells, the chemical reduction process is the most convenient and inexpensive way of this one. For biomedical applications, we have to go for CVD or micromechanical exfoliation. And for EMI shielding applications or high strength materials, we can go by chemical reduction process. Okay, to start with, without any much sophistication, we can start with the chemical reduction process. And even though the some of the methods which we have discussed, which I have shown in the previous slide, looks very simple or very what is called inexpensive, but the process involved is very complicated in this system, because we are dealing with what is called atomic dimensions, which are already sub-nanometer scale. Okay, so people use this kind of multi-layer growth on metallic surfaces, and it's also possible that we can have a single layer growth on metallic phosphates, and we can also deposit on a substrate, and then you can just flexibly do this one by transforming to this structure to different applications. Okay, it is like those who are very familiar with the dosa making, right? If you have a substrate or a hot plate with a single material, where you can have varieties of products, like I hope you are all very familiar with that. And we have a thick layer, we call it as uttapam, or when you make a very thin layer, then we call it as roast, or we can have it as um, bulk kind of thing. We can also have directional growth, where people, the restaurants, they put as a conical kind of thing by just taking a thin layer of dosa and then rotating it and then make it as a pyramidal structures like that. So when we have the proper substrate, and it is very flexible to use this graphene, and it can be made in different kind of morphology or these things. But of course, it is not an easy process where everybody can do. But once we optimize the process, for example, you are more concerned about the number of layers, and also the angle through which the formation, and also large area. As I said, we have done some large area graphene, but it was not a single layer, but it was stacking up 2 layers of graphene like that. And also the uniformity. There are so many factors in there, because the ultimate aim is to have the production capacity, yield, cost, equipment, and production line. That is the most important thing, and whatever the methodology we follow for that. And of course, we cannot compromise the properties like conductivity, mechanical strength, and optical properties, mobility, and also thermal conductivity. These are the major process optimization involved in the graphene synthesis. As I said, we have a variety of methods, and some of them are very trivial, and some of them are very complicated process, and some techniques need a very sophisticated method, equipment kind of thing. I'll just give that a few techniques which are all very simple to use it in the laboratory scale, especially for beginners or those who wanted to start this synthesis process. The best way would be to follow the chemical reduction process, where you take natural graphite as the source material, and combined with the very strong acids like H2SO4, HNO3, HCl. Any strong acid will do. And then we have to add deliberately the oxidizing agents to introduce the oxygen functional groups, because once the oxygen functional groups are introduced, the layered structure becomes very prominent and also very flexible, so that it is easy to separate the layered structure. And after drying in vacuum for about a few hours, then you get the graphene oxide powders. And once you have the graphene oxide powder, which can be mixed with water and sonicated for about 1 hour, you get the graphene oxide dispersion. Okay, now this dispersion can be mixed with reducing agents. There are plenty of reducing agents available, which we have been using, like thiourea is the reducing agent, and reflex it at 95 degrees Celsius for 12 hours. You get what is called reduced graphene oxide. And because this graphene oxide will have oxygen functional groups, and if you are able to get rid of all the oxygen functional groups, then it becomes graphene. But many a time there will be skeletal residual oxygen functional group present in the matrix, and therefore we safely call it as reduced graphene oxide, okay, RGO. And once you prepare this one, The best way to check the reduction process is the FTIR, and this is actually the graphene oxide where you have the different kinds of oxygen functional groups like hydroxyl, carboxyl, epoxynyl, and carbonyl groups. And when you do the reduction process with thiourea or any other reducing agent, and you get rid of almost all the oxygen functional groups except a residual functional group here, and this is actually the skeletal migration of graphene, and this becomes RGO. And if you are able to reduce this particular oxygen functional group, then it becomes a graphene. And to check the formation of the graphene, the best way would be to check with the Raman spectrum, where you have the D band and G band peaks. And if you have a single layer, you get only the G band and you don't get the D bands. And if you have a stacking of layers with very uniform thickness, you will be getting these overtone peaks like 2D and D plus G peaks. And once you reduce this one, and obviously we check the thermal stability, and you can just see the thermal stability of reduced graphene oxide compared to graphene oxide, because graphene oxide is stable only up to 200 degrees Celsius with weight loss of around 20 degrees Celsius, 20%. Whereas the RGO is highly stable even after 800 degrees Celsius, the weight loss is only less than 40%. And these are all typically the structures which we look, and this is actually stacking up few layers of graphene, and this is actually the edge which shows almost a single layer graphene, and this is actually the FFT, fast Fourier transform image, to confirm the crystallographic orientation of the structures. Okay, so this was our initial what we did, and then we checked the electrochemical performance. And for pure graphene oxide and the graphene, you can just see the graphene oxide, the maximum current is of the order of 800 microampere. And for the reduced graphene oxide, it becomes almost twice that of this value. It's almost 1600 microampere. And the specific capacitance measured using this formula is about 800 farad per gram. And this is looks that this electrode is very stable, where we can achieve very high energy density. But looking at the current value, which is of the order of microampere, and it will be difficult to achieve a better power density for this kind of electrodes. And that's what we try to move from the pure graphene to composite structures. So in order to make the composite structures, of course, we can try with the chemical reduction, but because of the multi-component nature of the composite structure, it will be very difficult to optimize the conditions for by chemical reduction process. So therefore, we can go by solvothermal synthesis, and solvothermal synthesis involves a reaction in an autoclave. This is a stainless steel autoclave, which I'm sure that many of you are very familiar with. And the structure of the autoclave is basically this is actually a stainless steel autoclave, and you have a precursor solution that which is covered with the Teflon liner, and then we have the stainless steel lid, and then this is the pressure seal, because this involves a slightly elevated temperature and pressure. And the parameters optimized to be optimized for the synthesis is the reaction temperature, reactant time, selection of the solvent, and the suitable surfactant to have the control of the growth, and then the precursor type, and what kind of precursor, whether it's organic or inorganic, or the combination of these two. That's also important. The advantage of this solvothermal method is we can very precisely control the size and shape of these particles or the structures fabricated by this in situ process. And because it involves slightly elevated temperature and pressures, then we can do the molecular mixing at the molecular level, and which ensures that stoichiometry, and then we can achieve also better crystallinity, and bulk synthesis is also possible if you have a large volume autoclave. And the material which we use, we can prepare using this autoclave is not only the two-dimensional platelet structures, we can also prepare quantum dot structures or one-dimensional nanode structures like tubes, wires, or whiskers, filament, fibers, or we can also use three-dimensional bulk nanostructures like nanospheres for using this allothermal technique. And this allothermal technique has been very effective in making even heterostructures also, which we have made some attempt for that. So we started preparing the composite structures using by allothermal synthesis, and we tried with reduced graphene oxide with the tin oxide nanoparticles. Actually, for a very specific purpose, we also make a polymer coating on the composite, and this is actually the graphene 2D layer, and then this is actually the integrated tin oxide nanoparticles, and you have the PMMA coating over the surface. Okay, and this is actually the microscopic image of the surface, looks like that, and then the FFT image shows that you have the 002 orientation of the graphitic piece, and then 101 corresponds to the tin oxide nanoparticles, and 211 is actually the lattice pattern for this PM polymer. Okay, so for this electrode, we just try to check the CV, cyclic voltammetry, and you can just see the previous case, it was only the microampere, and then for this electrode, we get what is called the milliampere range of current, and you can just see the CV, which shows more or less the rectangular curves with the different scanning voltage from 2 millivolt per second to almost 100 millivolt per second. So this was actually partly done by allothermal synthesis, but because of this PMMA coating on the surface, and we could not get the better performance for this the surface area for these structures. Okay. Then we tried with the different metal oxides, and this is actually reduced graphene oxide and cobalt oxide nanocomposite. This was also done by in situ reduction process using allothermal synthesis, and it was a bulk batch of around 30 milligrams of graphene oxide, which was mixed with this cobalt precursor, and then the in situ reduction used this formation of graphene and metal oxide to form one. And because this was done by very random way, by in situ process, we observed very interesting morphology of this cobalt oxide particles, which are all spherical particles, which are all isolated with uniform size. Then in some places we observed a kind of pyramidal, hexagonal and pyramidal kind of structures, and somewhere it's becoming a clustered surface. So this is actually the morphology where we have the isolated and then pyramidal structures, and this is the lattice patterns of this one, and the imaging shows that we have the distribution of carbon, cobalt, and oxygen very uniformly on this surface. Okay, and this electrode was also subjected to CV and chronopotentiometer studies, and of course the XPS also confirmed the presence of cobalt and carbon in this electrode system. And here also the current is of the order of milliampere range, and when we do the cyclic stability, we observed that the cyclic stability is achieved up to 96.6% even after 2000 charge discharge cycles at an applied current of 10 ampere per gram. And the specific capacitance for this sample is around 487 farad per gram with 5 millivolt per second, and it is 295 farad per gram with 1 ampere per gram current density. The energy density and power density were calculated from this Ragana plot, and the energy density is about 44.53 watt hour per kg, and the power density is very good, like 285 watt per kilogram. Okay, so having done these kind of things, we tried to move with ruthenium oxide. As I said, ruthenium oxide is a stable binary oxide, which can be easily integrated with different kinds of polymers or carbon-based materials also. And this was also done by in situ reduction process by solvothermal synthesis. By adapting this protocol from ruthenium chloride, hydrate is the starting material, then we added citric acid solution, and then it was the yield was around 0.1 gram of graphene oxide, and from this we just try to reduce this one, and then we get what is called RGO, graphene nanocomposite. Okay, and sorry, ruthenium oxide graphene nanocomposite, and this electrode was tested where we can this is for milliampere range of current, and actually this metal oxide was just coated on the electrolyte, and if we have the pure graphene oxide, then we have the we have the graphene and RGO, then it becomes a composite. And ruthenium oxide itself is a very stable electrode, so we just tried and then compared the performance of this composite electrode as well as pure electrode. And the stability of this electrode was tested for about 100 charge discharge cycles. Then this is the Ragana plot where we confirm the power density as well as the energy density for this electrode is better than pure ruthenium oxide as well as pure graphene oxide. Okay, this is the composite electrode performance. Okay. Then we tried with the titanium oxide, and this titanium oxide was very uniformly integrated with this 2D graphene layers, and because of the uniformity, and you can just see the performance is better where we achieved the current density of the order of ampere per gram. And with this current density and the current density and also the cyclic stability, we made a 2 electrode supercapacitor, which is called a flexible solid state supercapacitor. Then we studied the performance, and here also you can just see the pure titanium oxide doesn't show any hysteresis, and the graphene oxide has a better value, little bit, and whereas the titanium graphene composite will have a very clear CV curve with a large integral area, so that this means the capacitance can reach the maximum for this kind of electrodes. This was actually a 2 electrode real working supercapacitor. Okay, the performance I'll show you at the end of this one, because that we have categorized as the functional device fabricated there. Then we also use vanadate, bismuth vanadate with the RGO, and this was also prepared by in situ reduction process. And here the uniqueness is that bismuth vanadate forms as a one-dimensional structure, and this gives the real connectivity between the 2D layers, so that you have the large mobility of the ions which move in a very guided path when it moves towards the electrode. Okay, and this electrode also has the current of the order of ampere per gram, and because of the one-dimensional structure and also the randomness with which this was integrated with the 2D layers, then we get a very distorted CV curve. But nevertheless, the performance is good, where we get the almost 100 and 500 farad per gram, and the stability is also good for this composite compared to bismuth vanadate or graphene oxide structures. Okay. Um, then we tried with, having done with metal oxides, we also wanted to try with metal sulfides. And the metal sulfides is like we tried with the cadmium sulfide, zinc sulfide, lead sulfide, and RGO. The advantage is that these metal sulfides can be prepared as a tiny material, because these are all known for their quantum dot formation. And these tiny quantum dots can be easily integrated with the 2D layered reduced graphene oxide. And this is the typical schematic of this structure. And the Raman shows that we have the very perfect formation of this graphene cadmium sulfide composite with G beak, which is almost equal to D beak. And more than that, because of the cadmium sulfide particles, and we have the first order, second order, and third order longitudinal optical phonon modes, which are also clearly observed in this structure. Okay, this is basically very significant for the cadmium sulfide quantum dots. And even if these quantum dot structures are integrated with the RGO, still we have this clear observation of the different longitudinal optical phonon modes, and which confirms the what is called the sensitivity and also purity of these samples, electrodes. And the structural studies were also carried out, and then we also did the FTF for that. And this is the thermal stability for this cadmium RGO, and this is actually the RGO particle in cadmium sulfide quantum dots integrated on two-dimensional graphene. And the XPS confirms the presence of carbon, cadmium, and oxygen. And this is an interesting observation. For example, cadmium sulfide has a very strong luminescence peak at 578, 580 nanometer. But when we combine this cadmium sulfide with RGO, and the luminescence drastically reduces, or it becomes what is called luminescence punching. Okay. And this observation was again confirmed with different materials like lead sulfide, zinc sulfide. In all these aspects, we got the similar results. And the one reason for this is like when we have the graphene and the metal oxide, metal sulfide, cadmium sulfide, the Fermi level, Fermi energy is more or less same for the graphene, which is about 4 electron volt, and cadmium sulfide is about 2 electron volt. And also the what is called the surface interaction, surface strong, very surface activity of this cadmium sulfide sitting on the graphene is also very strong, and therefore we observe this kind of luminescence quenching. Okay, so this is actually the CV, and the CV for pure cadmium sulfide get a very clear oxidation and reduction peaks. And when we combine this cadmium sulfide with RGO, then we have the very clear CV curve with a very long, very high integral area. Of course, the oxidation reduction peaks are also just appeared in this kind of thing. For this electrode, actually, we have observed the current is of the order of milliampere, and then the capacitance was around 600 farad per gram. Then we also tried to do the heterostructures, the metal molybdenum oxide combined with reduced graphene oxide. And this kind of heterostructures are formed like this. You have the graphene, molybdenum disulfide, graphene, molybdenum, the alternate layers. This was also done by hydrothermal process, where you take the graphite, natural graphite, and then convert it into graphene oxide by modified Hammers method, and then mixed with molybdenum source, and then the reaction is at 180 degrees Celsius for 24 hours. You get the formation of these 2D layered structures, over which we have the MOS2 formation. And the structure looks like this. You have the base is 2D, and then the black parts are basically MOS2, and this is actually the schematic, and this is actually the actual um, edge of the structure, with the edge where we have alternate layers of graphene MOS2, graphene MOS2 like that. Okay. And this electrode was also prepared, and then the performance was studied with um, the current densities of the RF ampere per gram, and which confirms that this kind of 2D heterostructure electrodes can have a better specific capacitance, and also the power density and energy density kind of. Okay. Then we also tried to do, this is the stability which we have tested for this one, and the power density and energy density for these heterostructures. Compared to graphene oxide, the MOS2 has a better one, and even compared to MOS2, the composite has a better power density and also energy density. Okay. So then we also try to do the multi-component system by the combination of three-dimensional bulk cerium oxide, then mixed with the two-dimensional reduced graphene oxide, and integrated with one-dimensional CNT. Okay, so this is like CNT, graphene, and then this is cerium oxide. You have the combination of these three, and which was also prepared, and the structure looks like this, and it also gives a very stable electrode, and this works with salt and other liquid electrolytes. With the performance was very good, and current density is reached again of the RF ampere per gram, and this is from ranging the voltage scan from 5 million volt to uh, 0.5 ampere per gram to 2 ampere per gram, and the specific capacitance for this was this is actually two electrode structure with the RGO, CNT, cerium oxide. Another one is CNT, cerium oxide. You can just see this is more or less comparable, and the specific capacitance is about 220 farad per gram. And we tried with different multi-component system, and this is reduced graphene oxide, MOS2, and cobalt oxide nanocomposite. This was also done by in situ reduction process. You have the exfoliated graphene oxide mixed with manganese source and the cobalt source, and sintered at 60 degrees Celsius in oil bath for about 30 minutes. Then you have the formation of these structures, and then calcinated at 300 degrees Celsius for 5 hours. You get the stable electrode system like this, and this is actually the elemental mapping of the material with what is called cobalt, manganese, oxygen, and other species. And you can just see the HRTM images shows a very clear demarcation of the lattice patterns for this metal oxide, as well as the two-dimensional base. And the current density for this kind of electrode was also of the order of ampere per gram. And the elemental mapping confirms that we have the uniform distribution of this cobalt and manganese on the 2D layer. And the stability was also very good. It's almost reaching around 81% for the manganese, and this is for the composite electrode. Okay. This is actually the last part which I just wanted to focus on, the large area graphene sheet. And this is actually the normal graphene oxide synthesis by modified Hammers method, using the natural graphite as the source material, and then strong acids like H2SO4, KMNO4, and H2O, HCl. And by centrifugation process, we get the fine graphene oxide material. And after this, if you go for a chemical reduction process, you will not be able to retain the physical structure of this one. So actually, then in order to reduce the graphene oxide, we have done the inert atmosphere annealing using argon and nitrogen atmosphere. And so this was done in a controlled manner. And the formation of this large area was, we have the graphene fine oxide slurry, and which was poured in Petri dish plate, and then we formed the graphene oxide sheets. And once the graphene oxide sheet was reduced with the inert atmosphere using argon and nitrogen atmosphere, then we get the reduced graphene oxide. And this was done by what is called this was done by in situ process, but the formation is more a kind of self-assembly process, where you have the graphene oxide and then it is sonicated and then poured on a Petri dish. And before pouring onto the Petri dish, a silane coating was done on this Petri dish, so that after formation of this electrode paper, it was easy to peel off from the surface. And after the silane coated on the Petri dish, then we have the graphene oxide slurry, and then it is just heated at 95 degrees Celsius for about 2 hours. Then you get the graphene paper. And this is actually the formation mechanism of this one. And the thermal stability was also tested with the different temperatures, and the stability is also more about 500 degrees Celsius annealed sample. And before fixing the annealing temperature, we did some molecular simulation studies, because when you just look into the XRD, for this is for 350, you have some residual oxygen peak, and this is for 400, and only for 450, 500, 550 we don't get very impurity peaks. And this is good for both argon atmosphere annealing as well as the nitrogen annealing. In both the cases, we have this formation, and then it is things. And once you optimize this one, for example, at room temperature, you can just see the perfect molecule. At 400, then the formation is very intact. As well as nitrogen atmosphere. And this is the Raman, where you can just see the D and G band with the prominent G pack, which peak, which shows the high purity and also the homogeneity of the structure. And the Raman imaging shows we have the GOD band, RGOD band, and RGOD band kind of thing. And this is actually the morphology of this one, and the structure is almost 10 square centimeter, 10 centimeter by 10 centimeter, and this is the microstructure of this one. As I said, the thickness of this was, the film was around 15 nanometer, micrometer, and we tried to optimize the conditions to reduce the thickness, but it was a real challenge because it forms by the self-assembly process where we have some limitations on control of this parameter. So we have some kind of macroscopic voids and defects which are observed in this bulk structure. So otherwise, if you look into the edge also, the structure is very uniform, and we have some kind of folded layered structure observed for this material. Okay, and this is the selected aerial conduction pattern. And these are all highly flexible. Okay, for example, we can this is the structure, and then we can just flex it, roll it, and even stretch it. It doesn't lose its physical stability, and that is the reason why we this can be used potentially for the flexible solid state supercapacitor formation. Okay, and this is the current of the above milliampere for this electrode, and then the specific capacitance is almost 500 farad per gram with the scan rate of maximum 20 millivolt per second. And this is the charge discharge curve, and you can just see both for argon as well as the nitrogen atmospheric annealing, and the charge discharge curves looks very perfect. So that means compared to the previous research where the bulk particles leads to a kind of curved or a kind of oriented towards one direction, whereas this stacking, and the stacking is separated with a very narrow interface layer, and it shows a very perfect symmetric charge discharge curve. Okay, and as I said, using these flexible structures, we have fabricated the flexible solid state supercapacitor, which is, for example, you take the two different papers and then roll it with polymer separation. Then it becomes flexible supercapacitor, and flexible supercapacitor is tested by glowing LED attached with this one. And we also measure the conductance of these different stages, like room temperature 400 and 500 degrees Celsius, and then the specific capacitance retention was also tested after 1000 charge discharge cycles, and which is almost a very good specific capacitance retention. Then we tried different fabricated different functional groups, functional devices, and this was actually fabricated electrical actuator, right? For example, this is your anode, and this is your cathode, and then it is separated by the polymer separator, and the device is taken this, and this is actually the substrate. Okay, and with this very tiny substrate, if the tip displacement for both the negative as well as the positive bias for these PVA, H3PO4 and PVA naphthalene solutions were also very studied, and with the in both the cases, both negative as well as positive bias, the tip displacement is very prominent, and we have just applied a pattern for this work, and since I have very limited information about this material. Okay, and another interesting application is about the usage in perovskite solar cells. Perovskite solar cells, the major challenge is like the stability of the perovskite layer, and also we have to have the whole transport layer and then metallic layer separately on this. And for example, if we have FTO substrate, or which we have titanium oxide, then which is coated on coated with perovskite layer, and over which again you have to go for a metal oxide and then FTO. But instead of this, what we do is that we can have the boron doped RGO paper, which is coated on this perovskite layer, and then we have the easy cold transport possibility for from this ceramic, sorry, the perovskite structure. And the requirement for the boron doping is the boron doped RGO is more better stability, and also the cold transport capacity is very high for compared to pure RGO. And also we did some other work for with different boron doping on pure RGO. The performance for higher boron doping was very high, and therefore we used this one to to check the cold transporting property of the perovskite layer, and also we studied the JV curve for this, and we achieved the photoelectric conversion efficiency of about 5% for the 20% boron dope, and sorry, 40% boron dope compared to 20% boron dope samples. Okay. Then we also did the ammonia sensing, because ammonia vapor sensing is basically the dynamic process. Ammonia molecule sensing is very easy, but ammonia vapor sensing is very things, and we need to have a very perfect calibration system to check the ammonia vapor sensing. And we have used this reduced graphene oxide pure as well as cerium oxide doped and tin oxide doped structures. For pure RGO, the sensitivity was only 23.28%, and whereas tin oxide doped RGO, the sensitivity reached almost 41%, and the cerium oxide RGO has the higher sensitivity of about 51% for ammonia vapor sensing. Okay. Then we also tried with the ozone sensing and other sensing process using this RGO, but because of the lack of time that I restrict with this. And to summarize that we have been working on these 2D graphene sheets and graphene metal oxide composites prepared by modified Hammers method, and then chemical reduction process, and also the composite formation by solvothermal synthesis. And we have observed the improved electrochemical properties for metal oxide two-dimensional layered composite, especially for MOS2 and ruthenium oxide composite structures. And we also tried the multi-layer composites for three-dimensional bulk cerium oxide with two-dimensional graphene, and integrated with one-dimensional carbon nanotubes. And those kind of structures were, electrodes were highly stable with the improved electrochemical and high specific capacitance. The graphene bucky paper, large area paper, have also been prepared, and then with the flexible structures by reduction in argon and nitrogen atmosphere instead of chemical reduction process to retain the physical structure. And different functional devices like solid state supercapacitors, bimorphic actuators, perovskite solar cells, and ammonia vapor sensing performance have also been studied. Okay, so to acknowledge, we have some collaboration with the National Institute for Material Science, Japan, and also the University of Newcastle in Australia, Professor Ajay and Vinu. And actually, the students who have done this work is Dr. M. Sanmugam, Dr. Thangappan, Dr. Nagaraju, Dr. Sengotai, and Dr. Sellakumar. All of them are now in Sanmugam is in Korea, and Thangappan is a faculty in Periyar University, and Sengotai is in Japan, and Sellakumar is working in a college in Coimbatore. So we have funding from DST Nanomission program and CRP funded project. Then we have MHRD STARCH project also. And part of this work was done as NIMS Anna University Joint Graduate School program, through which both Sengotayan and Sarmugam, they spent almost 1 year in the National Institute for Material Science, Japan. Okay. So with this, let me thank you one and all for very patient hearing for almost 2 hours. And I will be happy to clarify if you have any questions or clarifications. Okay, we have another 5 minutes to go. Hello.
Yes.
Please. Sir, I'll be happy if you have any questions or clarifications.
Of course.
Yeah.
What about the participants? If they are interested in this, they can raise the question. Otherwise, due to time shortage, you can post the questions to the chat box and we'll forward it to the resource person and you can get that information from them.
Okay, sir. Fine.
Before going to the conventional vote of thanks, I personally thank Dr. Jaywell for this, Anna University for this program. Actually, I am a proud product of Anna University. I have completed my MPhil Medical Physics in Anna University. Of course, I was the contemporary to Dr. Ganeshan, registrar, former registrar, and Sashri Kumar. I was there in that particular period, and I have completed my MPhil under Dr. Yesan sir. And so I recollect all the information regarding Anna University. Of course, Aruna was my junior at that time, so we had that exposure in medical physics and ultrasonics. We had it. So I take this opportunity to recollect all the information regarding Anna University. Thank you, sir, for getting me to the nostalgic information regarding Anna University. Of course, we are in the that concluding session. Actually, for the past 2 days, nearly 400, 500 participants. Of course, they are along with us. Thank for all the participants first, because without you, just we can't have that much success in this regard. And the resource persons also, we are that much impressive. So only this much a good number of people we had. So I take this opportunity to thank everyone for this. And we have the regular and formal vote of thanks. It is a part of DBT, Department of Biotechnology program, staff, actually faculty development program, we have it. Now, Dr. Ishaq Ahmed will go for the conventional vote of thanks. And report also, report for the past 4 sessions, what happened in the 2 days, just he will spare the information regarding. And on behalf of our Department of Physics, Jamal Mohamed College, and of my own behalf, I thank everyone who have participated, and over to Dr. Ishaq Ahmed. Thank you.
Dear resource person and all the participants of this 2-day faculty online development program on condensed matter physics. As a convention, I'd like to give a brief report of all the activities that had taken place in these 2 days. This online faculty development program was organized by the PG and Research Department of Physics in association with the Internal Quality Assurance Cell of our college and in collaboration with Indian Spectrophysics Association, Chennai. Dr. S. Gunasekharan, Dean Research and Development, St. Peter's Institute of Higher Education and Research, Chennai, and founder of ISPA, Indian Spectrophysics Association, inaugurated this session. In his inaugural and keynote address, he explained the key aspects of condensed matter physics and the role it has played in technological development. That 25 Nobel Prizes have been awarded to condensed matter physicists for the past 20 years is a live testimony to this importance of condensed matter physics. He also highlighted the contribution of Dr. Albert Einstein, the renowned scientist Albert Einstein, who made 3 epoch-making discoveries, namely Brownian motion, photoelectric effect, and theory of relativity, all in a single year, 1905. Rightly has he been claimed as the father of solid-state physics. Dr. S. Gunasekharan also noted with pride the golden decades for Indian physics, namely the 1920s and 30s, with 3 Indian physicists making notable contributions and additions to science in the form of discovery of the Saha equation, the Bose statistics, and the Raman effect. To the young scholars, he advised them to have an intense interest in their chosen field and try to find applications in their fields of study. Railing out from statistics, he pointed out the standing of our country in the terms of scholars pursuing research, publications, H-index, etc., and the necessity for both improving quality and quantity of research. Further stressing the importance of condensed matter physics, he pointed out that 35% of research articles in physics are from this field. And as a proud Tamilian, he said that Tamil Nadu stands first in the country in terms of enrollment of students, of scholars for their PhD program. As the founder president of ISPA, he encouraged both the newcomers and seasoned researchers and offered all help that they might request from the ISPA for their research. The second session was on photon upconversion nanomaterials and their bioapplications. This was addressed by Dr. J. Senthil Selvan, Assistant Professor, Department of Nuclear Physics, University of Madras, Chennai. Starting from the principles of luminescence, our resource person explained the differences between the lasers, second harmonic generation, and upconversion luminescence. Further, he elaborated on the theory of upconversion luminescence, upconversion nanomaterials, and dwelt on the applications of these in various varied areas, in particular the field of biomedicine and medical imaging. His lecture was captivating, illuminating, informative, and sustained interest of all the participants. The third session, that is the first session today, was on oxide thermoelectric materials for energy storage. Our speaker resource person for this session was Dr. M. Arivanandam, Professor, Center for Nanoscience and Technology, Anna University, Chennai. He started his talk by pointing out the greenhouse effects, global warming, ill effects of melting of Antarctic ice glaciers, rising of sea and oceanic water levels, and concomitant disasters. He then went that is wasted can be converted into useful form, such as in autothermal electric generation, solar thermal electric generator, etc. Subsequent to this, he explained the basic principles of thermoelectricity, variations of thermoelectric properties of nanomaterials, strategies for improving them, in particular by nanostructuring, and then he went on to explain the search for phonon gas electron crystal. He then explained the characterization and synthesis and characterization techniques of oxide thermoelectric crystals. Applications. Our resource person for this concluding session, R. Jayavel, Director, Center for Nanoscience and Technology, Anna University, Chennai. He highlighted that materials form the backbone of all technological advances and applications regarding energy storage. He began his talk with different types of 2D layered nanomaterials and their applications in energy storage systems. He then explained the discovery and properties of graphene, the methods of its synthesis, and the enhancement in energy storage capacity by using graphene metal oxide nanocomposites. Dear participants, I hope all of you would have been enjoying these 4 sessions, and with your patience, this 2-day program has become a great success. Now let me proceed on to the next task assigned to me, the vote of thanks. The PG and Research Department of Physics of Jamal Mohamed College finds pleasure in expressing the gratitude to our Honorable Secretary and Correspondent, Dr. A. Khaja Nazimuddin, our respected Treasurer, Mr. M. Jamal Mohamed, our young and dynamic Assistant Secretary, Dr. Abdul Samad, for all the encouragement they have provided for all the activities of our department, in particular, this online FDP program on condensed matter physics. We would like to express our gratitude and sincere thanks to our principal, Dr. S. Ismail Moidin, who has been encouraging us in organization of this online program. We also express our thanks to our Vice Principal, Dr. A. Mohamed Ibrahim, and additional Vice Principal for Dr. M. Mohamed Shihabuddin for their encouragement and support. We'd like to express our thanks to our honorary member of College Management Committee, Dr. K.N. Abdul Qadir Nihal, as well as Directors of Hostel Administration, Dr. K.N. Mohamed Fazil and Mrs. J. Hajira Fatima, for their encouragement and support, help and support. We'd like to express our heartfelt thanks to our resource persons, Professor S. Gunasekharan, Research Dean, St. Peter's Institute of Higher Education and Research, Chennai, for delivering his inaugural and keynote address. Dr. J. Sendil Selvan, Assistant Professor, Department of Nuclear Physics, University of Chennai, for delivering his lecture on photo upconversion, nanomaterials and their bio applications. We would like to express our thanks to Dr. M. Arivanandam, Professor, Center for Nanoscience and Technology, Anna University, Chennai, for delivering his talk on oxide thermoelectric materials for energy harvesting. We would also like to thank Professor R. Jayavel, Director, Center for Nanoscience and Technology, Anna University, Chennai, for delivering his talk on 2D nanocomposite functional materials for energy storage applications. Dear sirs, you have helped us in organizing this seminar by your kind acceptance and have enlightened the participants with your knowledge and expertise. The PG Research and Department of Physics is specially indebted to Professor S. Gunasekharan for having entered into an MOU with our department and also taking the lead role in organizing this 2-day FDP online program. I would like to express my sincere thanks to our beloved head of the department, Dr. M. Jamal Mohamed Jafar, and all the colleagues in my department, in particular, Dr. S. Sheikh Dawood, the additional coordinator, departmental coordinator for DBT program, and other colleagues as well as support staff for their efforts and timely help. I would like to express my sincere thanks to all the participants who are with us for all the sessions with patience and interacted with the resource person with enthusiasm and interest. I would like to thank you, all of you, once again. Thank you.
certificates வந்து